record on this. Okay, here we go. This is Manual D duct design for HVAC tech. So I designed this class, and every time I give it, I modify it a little bit, try to make it better for people like you and me, HVAC technicians, small contractors, people getting started doing their own duct design and want to learn how to do it the right way. So just a little bit about me. Most of y'all know or follow me on Instagram or LinkedIn or Facebook, but here are some of my some information about me. I'm in North Carolina, and let's see. Jonathan requested recorded this meeting locally. I'm going to send you a recording of this. I'd rather not allow people recording it locally, just in case it gets out there. It wouldn't be fair to everybody who paid for the class. I promise you, you will get a recording of this. I just don't want to get out there where now, people that didn't pay for the class may get their hands on it. But I promise you, I will get you a recording, and then I can't stop you from doing what you do after that. So, all right.
Good. No worries.
Yeah, no problem. All right. So what are we going to get into? We're going to first start with static pressure, because we have to understand static pressure before we can understand duct design, airflow. We'll get into the manual D sizing method, which is approved by ACA. We'll talk about the ACA Manual D speed sheet, which is a way that you can, in the absence of software, at least you can get started and go through the Manual D process to get to the friction rate, which is that number that you put on your ductulator, and then you size ducts accordingly. We'll talk about best and worst practices, diagnosing duct problems. So when you're out there in the field, how do you know that you've got an airflow problem? How do you know that you will have an airflow problem once you swap out that equipment and it's now working with the existing ductwork? We'll talk about the most accurate tool to check airflow. And thanks to Chris Hughes and the Energy Conservatory for co-sponsoring this class, it made it a little bit more affordable for all of y'all. And they'll have Chris will have a chance to talk to you about what we both feel like is the most accurate tool to check airflow. We'll talk about some other ways to do it also. And finally, we'll do some questions from the field. And then after the class, when we stop recording, if you guys want to pop a top and trade some war stories, I got a North Carolina brew in the refrigerator that's chilling down, and we'll hang out. So let's get right into it. The ACA design process, ACA stands for Air Conditioning Contractors of America. They're an organization that sets standards, that does training. And everything starts with the Manual J. So I really want y'all to understand that if you're going to do a Manual D process, you have to start with the Manual J load calculation. That's going to tell you how much heat loss and heat gain that the structure, the house, is going to have. And then once you do that, you're still not ready to select the unit, because Manual J only tells you what the house is doing. Manual S helps you to match what your equipment to what the heat load is. So Manual S stands for system selection. And then there's Manual D, duct design. So only after you've selected the equipment are you able to talk about ductwork. But if you notice, there's a space in between Manual S and Manual D, and that is Manual T, the redheaded stepchild of the ACA process. And Manual T is a design reference. It's a technical reference, but Manual T stands for termination. That's grills and registers. That helps us to size them properly so that we get good throw coming out of the register, and we don't have excessive pressure drop. We don't have noise. We're not blowing air on people. And so that's a really cool technical reference.
Tim,
Yes.
you're real choppy on my end for some reason. Is it just me?
I need someone else to chime in.
Yeah, it was a little bit cleared up now, it seems like.
Okay, I'm sorry about that. Is this any better?
It's clear on my end.
Yeah, clear on my end too.
Okay.
It must be just me then.
My end.
Possibly turn your camera off. That it may be a bandwidth problem, and let me know if that works. Yeah, I'm seeing. Sorry, I've been missing the chat here. Okay. All right. It may be a bandwidth thing. So sometimes if you turn your camera off, your bandwidth can be reserved for the sound. Thanks for letting me know, though. All right. I do this just because I want y'all to know that I'm not the end-all be-all expert. I get my training from people that are a lot smarter than me. So one of the organizations that I suggest that y'all look into is the National Comfort Institute, NCI. They are a training and credentialing organization. They concentrate a lot on airflow testing, performance testing, and they're made for the contractor. I'm a member. There's tons of training there. Also, I'm sure y'all have heard of HVAC School and Brian Orr. Alex Meany, he used to work for WrightSoft, which is a design software. Now he does his own thing. I've gotten an opportunity to take a couple of his classes, and he is really awesome. So look him up. Ed Jonawat works for ACCA now. He helps write the manuals, I know, and you can look him up. He's been on the HVAC School podcast many times and just kind of absorb their knowledge. And finally, Allison Bales, Energy Vanguard. He's got a blog. He writes. He just came out with a book last year, A House Needs to Breathe or Does It? Tons of great information. Everybody who's here today cares about doing HVAC the right way. And these are some of the people that I learned from. This is how I stepped up my game. So by all means, feel free to take your phone out, take a picture of the screen, and look these people up later. But I always do that just because we are in the presence of greatness, and I am not one of them. But I've learned a ton from these guys, and I feel like that I can kind of put it all together so that you can absorb some of this in a way that speaks the language that we speak as technicians and contractors. So why is duct design important? Because airflow is important. Poor airflow is one of the leading causes of comfort problems. So when we go out and we do a service call, at least what I used to do before I got a little better educated, is I throw gauges on the unit. I'd immediately check what's my superheat, subcooling, what's my temperature drop. And then if all that looked okay, I was like, well, I don't really know what to do for you. What we're missing here is that airflow. We need to be able to test airflow because that is where the rubber meets the road. And so poor airflow is one of the leading causes of room-to-room comfort problems, people just feeling hot and sticky in their house. Yes, sometimes the unit's low on gas. Yes, sometimes the coal's dirty. But a lot of times after you've exhausted all those things, airflow is really what you should have checked first. Poor airflow also results in higher energy bills because the unit has to run longer. Especially with an ECM motor, and we'll talk about this later, it pulls more amps to do the same amount of work. And that ultimately results in early equipment failure, compressors going bad, blower motors going bad. Poorly designed and installed ductwork is hard to fix afterwards. Once they put sheetrock up, you're very limited in being able to fix that kind of stuff. So while everything is open and accessible, you want to do it right the first time. And it's also one of the hardest things to read accurately. And that's why I think a lot of technicians and contractors get away from thinking about airflow, because for years it's been really hard to take accurate readings quickly that we can trust. But that has changed now. We'll get into some tools that we can use to accurately read airflow. So what are our goals when we design a duct system? Well, we want to be able to deliver air efficiently, which means that we want to keep static pressure low so that our blower doesn't have to work that hard to push that air through the duct. We want to keep it quiet. Nobody wants to have to turn their TV up whenever the air conditioning comes on. And before I had this house built, we were in an apartment, and that's exactly what we had to do. It sounded like a freight train every time the unit came on. Anybody that's lived in like a double wide trailer, a lot of times you got to crank the TV so loud you can actually hear it better outside the trailer than you can inside the trailer when the air is running. And we want to avoid that sort of thing. Economically, keeping static pressure and velocity low, it reduces the needs for us to go get expensive, high efficiency fittings. We just use some common sense. If we oversize ducts, then our material cost is higher and unnecessarily. And so our profit goes down. And accurately, we want to get the right amount of air in each room. So we don't want to be dumping all the air in the first two rooms, and then on the opposite end of the house, we don't have any kind of airflow. So we want to be able to deliver the right amount of air to each room and keep people comfortable. One solid rule of airflow and duct design is we never want to blow air directly on people. Nobody likes that. But on the other side of that, we also don't want to have air stagnation where we're not moving the air enough in the room so that it just kind of sits there and hangs out. And then people don't feel that exchange of air. And then it feels stuffy in the room, they're uncomfortable. So the Manual D design process works. It's a step-by-step process that helps us achieve the right duct size. And so before we do that, we've talked about this already, we need to have already done a load calculation. So I may be throwing a lot of new stuff out here to some people, and I get it. It may seem daunting. It's like, well, I just want to learn how to size ducts correctly, and I get it. But we can't really do that with confidence unless we first figure out how much heat gain and heat loss out of each room we have. So a little bit at a time. If you start doing manual J's, then graduate to doing a manual J and a manual S, and then be able to understand the role that supply registers and return grills have. Once you kind of figure those things out, then you're ready to do a really accurate manual D. And so here are the steps. As you can see, we're going to start with total static pressure. We go on down the line. And towards the very end is when we actually size the duct. But there are some steps that we need to do first. So lots of rules of thumb here in the industry. I grew up setting the little duct calculator wheel to 0.1 friction rate. Maybe some of you learned 0.08, and then you just size duct accordingly. And let's be honest, it works sometimes. It works a lot of times, but it doesn't work all the time. Sometimes doing that still results in comfort problems. So when do you know when you shouldn't set it to 0.1 or 0.08? Well, that's what Manual D tells you, is it helps you arrive at the friction rate using math and facts instead of just guesswork. So I know that most of us have probably sized ducts to 0.1 inches, but Manual D is going to teach us the right way of achieving that friction rate. It may be 0.1, but as we're going to see, it may be actually far off from that. All right, so again, here are our duct design steps. One more time, we're going to go right through this process, and we're actually going to do it using a sample house, and it's actually going to be the floor plan of my house. It's not going to be exactly how I design my duct system, but we're going to do it for my floor plan. And essentially what we're doing in Manual D is that we're sizing the entire duct system for the worst case run. And if we know that we're sizing the trunk and the branch for worst case scenario, we know all the other ones that aren't as far or aren't as restrictive are going to be okay. In fact, if anything, we may actually have to damper them down. And so that's really the whole premise, is that we're trying to figure out which duct run is the worst case scenario. Sometimes it's the farthest run from the unit, but it isn't all the time. And we're actually going to demonstrate that on our sample project. So let's get right into it. Our very first step is total external static pressure. Sometimes you read it as total static pressure. And here's what I want you to think about it as. It is friction in the ductwork. It creates a suction in the return and a positive pressure in the supply. So think about this young man that's trying to eat his milkshake here. That he's struggling, right? He's really pulling hard on that straw. What is that doing to his cheeks? Well, it's making them implode. That's a really high negative pressure. Well, that's what happens in the return duct. And the more restriction that there is in the return ducts, the harder it's going to pull, and the more negative the pressure in that return duct is going to be. The opposite in the supply duct. The gentleman playing the trumpet is trying to force air through a tiny little opening. And so what are his cheeks doing? They're blowing up. He's got a positive pressure. That's the same thing that happens in ductwork when we're trying to force air through a restrictive ductwork. And so total static pressure, total external static pressure, is reading the sum total of both of those pressures, the negative and the supply. We're putting them together, and we get an idea of how much resistance to airflow that the fan and the air handler is seeing. So total external static pressure, we've got an air handler here. It's a heat pump air handler, as you can see. We got a coil, and then after the coil is a blower, but we don't have any ductwork on it. So when the blower starts running, we don't have any ductwork, so there's no external static pressure. There's nothing to depressurize or pressurize because there's no ductwork hooked up to it. So if we hooked up a manometer, well, first of all, we have nowhere to put our hoses. So of course, a manometer is going to read 0 inches. But total external static pressure is pressure. It's not the velocity pressure. It's not pressure of the air flowing through the duct. It's the pressure that's pushing out on all the sides of the duct, as we can see here. And so whenever you try to force air through ductwork, yes, there's pressure of air moving. That's called velocity pressure. It's the pressure in the direction of airflow. But then perpendicular to that, to the walls of the duct, that's called static pressure. So once we hook up ductwork to the unit and we turn the fan on, this is what happens to the ductwork. Now, maybe not physically. Sometimes you can hear that pop in the ductwork, and that's exactly what it's doing. It's the pressure inside the duct. But on our return side, we have a negative pressure, just like there's a negative pressure when you're trying to drink a milkshake. And then on the supply duct, there is a positive pressure, just like there's a positive pressure when you're trying to blow through a trumpet. And so what total static pressure is reading is the sum of those two pressures. Now, when you take a look at those two numbers, negative 0.2 and positive 0.3, you're like, well, wait a minute. I remember in math class that when we add a negative to a positive, you don't get 0.5. Wouldn't that equal 0.1? Yes, but we're not thinking about it like that. Let me give you a better way of thinking about it here in the next slide. All right, so what we're doing is we're counting how far apart these two pressure numbers are. So our negative side is negative 0.2 from 0. And our supply side, we got positive 0.3. So how many units of pressure do we have in between? How many tenths of an inch do we have in between them? 2, 3, 4, 5. That's how we get 0.5 inches. And it doesn't matter what our return on our supply static pressure is. For example, now we've got negative 0.1 in the return and positive 0.4 in the supply. The fan still sees 0.5 inches static pressure. And so it does not care where we get that 0.5 inches. As long as we have it, we're going to be able to predict how much airflow comes out of that fan. So that's how we arrive at total static pressure. We're reading the difference between our negative and our positive, and think about it in a scale of 0 in the middle, then you got negative on one side and positive on the other side. And if there's any questions like that, please speak up, raise your hand. This is sort of a basic thing. Like, we've got to understand static pressure before we can do anything else. So duct friction, air moving through the ducts are going to drag along the inner walls of the ductwork. So, for example, we've got our blower and we've got some ductwork on it. And this is sort of what happens to the air. It not only drags against the walls of the ducts, but it also kind of churns inside the ducts, especially near fittings and elbows. And then that churning, that turbulence, also is sort of like having a solid piece of something in the duct that's restricting flow. So duct air is sort of going to do that. And that was just, that's me attempting to do something on PowerPoint. So I apologize for the bad ductwork. But it's going to hug the walls, and it's going to there's drag on the walls of the ductwork. Yes, some airflow flows through the middle of the duct uninhibited. But if you notice, also around that turn there, that inner turn, it kind of really gets turbulent right there. And that turbulence creates restriction to airflow. And so things that make more duct friction are longer duct lengths, because you got more duct, more metal that the air has to drag against, more fittings. So if you have unnecessary elbows and turns and other fittings, that creates turbulence. And inefficient fittings. So for example, this 90-degree elbow with 2 sharp turns on the inside and the outside, that is a very inefficient fitting. And we're going to actually see what Manual D says how inefficient that is here in a future slide. So inefficient fittings, they create more duct friction. And so these are all things that we want to avoid. We can't avoid them 100%. I mean, we got to have some ductwork on there. We got to have some fittings on there, but we can be smart about it. And again, we are just trying to avoid having friction. So just like there's friction in that straw and friction in that little trumpet, to airflow, that's exactly what ductwork, fittings, and all the stuff that the air handler has to push and pull against. That's what it's facing also. And that friction also creates a back pressure in the ductwork, especially the supply duct. And so as you've got air that's trying to be forced through a duct, not all of it wants to go as easily. And so it sort of gives a little bit of a pushback. You can kind of picture it that way. And so that's really why we have pressure in our ducts. More friction in the ducts equals more static pressure. And that works on the supply side and the return side. All right, so let's do a sample problem here. We've already done our manual J, and we're a carrier dealer. So we're gonna select our manual J. Says that we need around 3 tons of coolant, and so we figure out, okay, our manual S, this FXD air handler, the 037, it moves the amount of airflow that we need it to move. So this is our air handler that we've selected, the FXD 037. We've determined that this air handler matched with a 3-ton condensing unit. This is going to heat and cool our house just fine. All right, so FXD 037. And what we do, this is an expanded cooling chart. This is sort of, we're not going to get into manual S, but this is sort of part of the manual S process, is that we're trying to match that air handler and the CFMs that we need it to move in order to satisfy our load. So let me go back, sorry. Let's say that our load for manual J, I think you guys can see my mouse, is 34,900 BTUs. All right, we select this air handler. According to this chart, when this unit moves 1,200 CFMs and it's matched with the right condensing unit, the total BTUs is 34,960. So that is really, really close here. Now, the other part of manual S is we have to make sure that sensible cooling and latent cooling also match, but this is not a manual S class. But what I'm saying is we've selected an air handler that says, okay, this FXD 037 at 1,200 CFMs moves the amount of heat that we want it to move. So we've selected this air handler, and we've also selected 1,200 CFMs. This is our target CFMs for the whole design. Well, the next thing we need to do is find the airflow chart for that air handler. So Carrier provides that for you. Some manufacturers are a little bit better about providing that information than others, but I use a lot of Carrier stuff in my classes because they readily give you this information. So again, we've got this FXD 037 air handler. We want it to move 1,200 CFMs. So it comes from the factory. Anybody who's a Carrier dealer knows that everything comes from the factory with tap 3, at least it used to when I was a Carrier dealer. So when we install this FXD 037 and it comes from the factory with tap 3 ready to go, if we are running 0.5 inches static pressure, which is sort of like the target external static pressure that everyone looks for, what is our CFMs? It's only 1,070. Well, wait a minute, we need it to move 1,200. If it only moves 1,070, we're not going to be able to heat and cool that house well. So we're going to need to get more out of this air handler. So what do? Well, we may be tempted to just hook up speed tap 5. And a speed tap 5, it would move at 0.5 inches static pressure. It would move the amount of airflow that we want it to move. But the problem is we're completely tapped out at speed tap 5. And so if anything happens, if we have to, when we actually get out to the job and install the system, if we have to jog around a structural beam or go around some plumbing or do something else that's going to create more duct friction, we don't have anywhere else to go on here. And so when we're selecting equipment and designing ductwork, we want to try to avoid selecting it for the highest speed for that reason. So what is our option? If we have to move 1,200 CFMs and 0.5 static pressure is kind of what it's going to be, but we don't want to have speed tap 5, what do? Well, one option may be to select instead the next air handler down. And so even though you've got a 3-ton matchup, everybody knows that there are matchups with a 3.5-ton air handler, sometimes a 4-ton air handler. And so sometimes it makes sense to actually step up to the next size air handler, because look what happens when we go from the 037 to the 043. Now at speed tap 3, we're actually moving a little bit more than what our target was. And we're doing it with room to spare. And so what you're going to find is there are units that have really strong blowers, and there are units that have weenie blowers. And everybody's trying to save money these days. And what I'm finding is that's really hard to ask a unit to move the nominal CFM per ton that we're usually thinking about, 350, 400 CFM per ton. I'm looking at a lot of these blower charts. And these manufacturers putting these little weenie blowers in there because nobody wants to spend money building a unit. And it's actually making that airflow at like 0.4, 0.5 static pressure. And so if you've got a duct system that's going to require you to have more static pressure on it, that unit ain't going to cut it. You're going to have to actually step up to the next size up air handler. And that's unfortunate. Some units are better than others. But this is what may make sense. So I bring this slide out just to let you know that you want to know your equipment. If you're a Carrier dealer, you want to know what that FXD 037 can do. And what you may find is that you're going to stop selling this air handler with a 3-ton condenser. Instead, you're going to start selling this matchup here because it just delivers the air a lot easier. All right, so I want you to think about our 0.5 static pressure. This is sort of the target static pressure that we would like for the system to be designed for. Not every duct system is going to allow us to design it for 0.5 external static pressure, but they really work well when you do. But some houses, if you're trying to push air through a bunch of ducts that are kind of small to begin with because the architect didn't give you enough room, and maybe it's a zone system where you got an air handler in the basement and you got to push that air 3 stories up, you're going to end up having a little bit higher of a static pressure. And we'll talk about that a little bit later. But let's say that we're going to attempt to design a system for 0.5 inches static pressure, total external static pressure. I want you to think about that sort of like your paycheck. This is your gross pay when you look at your pay stub. Everybody knows the difference between gross pay and net pay, right? It's a pretty big difference, unfortunately. So the reason why I bring that up is because the next thing we're going to talk about, after we select what static pressure that we would like to design the system for, the next step is component losses. And so our external static pressure is sort of like our gross pay. Man, it looks like we made a lot of money, right? But then what happens? Taxes come out, right? And that is sort of like the component losses. Components are anything that's in the duct system that didn't come with the unit, that didn't come shipped with the unit. So it's things like diffusers, dampers, media filters, return grills. If you put in a furnace, you got a case coil. If you put in a heat pump, even though that little heater is inside the air handler, it didn't come shipped with the air handler. And so that is a component loss. And these things start knocking down the pressure as soon as it comes out of the fan or before it gets to the fan. And so it's sort of like what taxes and whatever other stuff you guys have that may come out of your check, child support, whatever it is, that's what kind of gets knocked out of your paycheck. And what's left is your net pay, which is what I want you to think of as available static pressure. So we started off with an air handler that could make 1,200 CFMs at 0.5 inches total static pressure. But we got all this non-ductwork stuff that we have to push air through. And it's only then do we have a little bit of pressure left over that we can actually design our duct system after. So I'll show you what that means in a future slide. So anything that didn't come shipped with your air handler is a component. So it has a component loss or a component pressure loss, a pressure drop. All right, this is what I'm talking about. We got our air handler, right? All right, this is a furnace because our air handler is right here at the return. Furnace has a heat exchanger. I need a little bit of audience participation, so anybody feel free to speak up. Do you think that the heat exchanger in a furnace is considered a component where we have to figure out what the component loss is?
No.
Built into the furnace.
Built in with the furnace, that's the rule. Anything that didn't come shipped with the furnace is called a component loss. If it came shipped with the furnace and installed, well, when they tested it at the factory, and they developed that airflow chart that we just got done looking at, they included this thing in there. So you're right, a heat exchanger is not a component loss, but the return grill is, and Manual D says that it has a component loss of 0.03 inches static pressure. If you are trying to improve indoor air quality, like hopefully everyone's trying to do, maybe you put in a media filter. Well, those can have a huge component loss. This is actually a very conservative component loss for our system, 0.1. A lot of media filters drop a lot more pressure than that. If you put in a furnace, you probably got a case coil, unless you live somewhere really, really cold where no one needs air conditioning. And you're going to have a component loss on that case coil. And that's actually a very conservative component loss for a case coil. Every system should have a damper. Now, you're not going to include all your dampers, because what you're doing to manual D is you're looking for the longest run or the worst case scenario run. So your air is only going to go through one grill and through one damper. You're not adding all your grills and dampers together. And finally, you're going to have a diffuser. This is a commercial diffuser. I should probably put a residential one in here. But Manual D says that these grills, dampers, and registers here are going to, you can use a rule of thumb of 0.03. The other things, we actually need to look them up, and we'll talk about that. So component pressure losses, when we add all these component losses up together, we 0.03 plus 0.10 plus 0.15 plus 0.03 plus 0.03, we get 0.34 inches of component loss. So now we can finally calculate our available static pressure that's available for the actual ductwork. Again, we haven't even considered any ductwork to this point. So again, our static pressure, our total external static pressure, felt pretty good, 0.5 inches. But then we took our component losses out, and what we're going to find is we don't have that much available static pressure left. But that is going to be our budget for our ductwork. So let's do the math. Available static pressure equals our total external static pressure minus our component loss. So paycheck minus taxes. We started out with 0.5. We had to take 0.34 taxes out, right? That only leaves us with 0.16. This is what we have to design the rest of the duct system for, is 0.16. So as you can see, most of your pressure drop that this unit is having to fight against is going to happen in the components that have nothing to do with ductwork. And that's something that's often missed. So available static pressure is the static pressure your entire duct system is allowed. So now let's get into how much static pressure drop we're actually going to have in our duct system. Our duct run length. So obviously duct run has a lot of a length of duct run is going to have a certain amount of resistance to it. This is where I suggest that y'all use some software, because it sucks doing this by hand. It sucks using the speed sheet that we're going to use tonight. The only reason why I'm using it is because I would have to teach you how to use this software in order for me to teach you Manual D from this stuff. This is very, very easy, but I do not recommend that you stay using this. The Manual D speed sheet is free. It works, but it is very tedious. But here's some of the HVAC design software that's out there that also includes ductwork. RightSoft, I've been using RightSoft for a long time. It works very well. I am also of the 90s window generation. If you are younger than 35, you're probably going to look at this stuff and be like, oh my God, what is this? This is so old.
Yeah.
Right. Yeah. Somebody knows what I'm talking about. Elite software, kind of the same thing. They work once you learn them. They're not easy to learn, but once you learn them, they work great. And RightSoft has a lot of features that I need as a designer when I'm doing lead jobs, Energy Star jobs, and that sort of thing. Here's the software I really want you guys to check out. Oops, sorry. Quick Model 3D. This is developed by somebody that's been in the trade for a long time. You actually draw the house in 3D. You actually draw the ducts in 3D. So if you have not yet learned and gotten sort of stuck committed to some of these, if you're just starting out, I really want you to check out Quick Model 3D. It really works well, and it's been around for a few years. They've worked out a lot of the bugs. So that's really a good choice. If you're just starting out, this is free. I think I left a link in the meeting notes and the invite. If not, I can send it to you later. We're going to go through the Manual D process using the speed sheet, but as you can see, it's probably going to be pretty tedious. All right, so this is what the speed sheet looks like, and here are the instructions. The bottom tab. This is again, we want to. You're welcome, Russ. We're going to read the fantastic manual. The first thing we're going to do is go to the effective length tab, and we're going to enter up to 4 supply runs to determine the longest equivalent run in the system. Enter the linear feet of trunk and run out ducts in the length sections for the supply ducts. Okay, a lot of words. Here's what it means. We're going to go into this effective length tab, and we're going to pick 4 supply runs that we suspect are going to be that worst case scenario. And then the speed sheet's going to actually tell us which one of the 4 is worst. Okay, so here's the basic layout of my house. I actually drew this on a WriteSoft, and this is not how I actually ran my duct system, but for the class, this is what we're going to do. Let's say this is the project that we're working on. Here's our air handler all the way here at the end of the house, and we got to push air all the way here to the other side. I want somebody to unmute and tell me, if you just look at this plan, which one looks like the worst case scenario, just looking at the plan without any other information, which one looks like the longest run, the worst case scenario that we need to design ductwork for.
The master.
The master, yeah. You got to push air all the way down this trunk, all the way up here, right? And so, look, we got something in the chat. Yep, the master. Very good. Okay, let's see if it's actually the master when we go through the manual D process. All right, so we're going to pick these 3 longest runs. Like if it ain't the master, it's probably the master bath, maybe the walk-in closet, because these are the farthest away from the air handler. But just for kicks and giggles, we're also going to throw in this breakfast one, because this is kind of a long run. Really, when we think about it, it's a long branch run. So we're going to throw that one in the mix also. And I'm looking at the chat, walk-in closet. Okay, we got someone for walk-in closet. All right, let's see which one it actually is. So we take and we measure out either on a set of plans, or we measure out on the job. If we're doing like a retrofit, we start taking some measurements here. And from the air handler to this termination, we start coming up with some lengths. So these are our total run out lengths. We have part of its trunk length and part of its branch length, but here's the total length. And here's what we're going to do. We're in the effective length chart here, and we're going to enter the 4 potential longest runs. So here's where we put the first one. This was for the dining room, which I think on the plan actually says breakfast room. Just know the breakfast room, dining room are the same thing. We had 25 feet of trunk, 15 feet of branch. We're going to do the same thing over here, and it's going to total these up down here, and it's going to automatically in the red pick which one is the longest length, which right now it's that master bedroom. So you guys have said master bedroom so far, you guys are right. Okay. The return, same thing. We just have a single return. It's about 10 feet long. And so it just brings it down to the bottom. So right now, master bedroom looks like it's the worst case scenario. Let's see if it stays that way. The next thing we get into in the manual D process, after we've figured out our longest duct run lengths, is our fitting equivalent length. Fitting equivalent length. What that means is every duct fitting that is in that system has a measure of restriction to it. And that restriction can be quantified to the equivalent of a straight line piece of duct. So say, for example, this collar that comes right off the supply plenum, when we just take our little circle cutter and we cut a circle in our supply plenum and we put a square or a takeoff on there, one of those airtight takeoffs, and we put in hopefully more than 4 screws. Hopefully we'll put mastic on it. We put that on there. It is saying that one little fitting right there, that little fitting that fits in a little box, is equivalent to 35 feet of straight line duct, because there is so much resistance that it takes for the air to come out of the air handler, bounce around the plenum, and finally figure out its way through that collar. So that's what Manual D is saying. You've got an equivalent of 35 feet of length just in that one little fitting. So here's what we're going to do. We're going to find all the fittings in our length of ducts, and we're going to find the equivalent length for them. We're going to put it in this effective length tab here. So we've got a fitting comes right off the air handler. Now I know we could use a squared around. Again, I've chosen this one to prove a point. But let's say we just, the same way the rednecks here do it, and I've done it for years. I just drill a hole in the side of my plenum, pop in a collar, right? All right, that's that guy right there. Next thing, we've got a trunk, right? Well, normally we just, again, cut a hole in our trunk and we just tap off of it. All right, here's where it gets kind of tricky. Manual D is saying that we need to figure out how many branches downstream of our collar that we have, because different collars with a different number of branches downstream have a different amount of equivalent length. So, for example, this is our fitting here. I want you guys to ignore this line, the 2N, because we're not using that. I want you to ignore 2O and ignore 2P. We're only worried about this row right here. And what it's saying is, if you've got 5 or more branches downstream of that takeoff, then the equivalent length of that one little collar is 75 feet. Now, if this is the end of the line and you don't have any transitions or reducers, you just have an end cap that follows that thing, it's 50. But again, you're going to have different numbers depending on how many downstream branches that you have. So, for example, this guy right here that serves the breakfast room or the dining room, how many downstream branches does it have? It has 1, 2, 3, 4, 5, right?
Need some reducers.
Yeah, if we put reducers, that would change things, right? But we haven't put reducers in yet. So
Using your velocity.
right, and we're going to get to reducers. But the point that I'm trying to make on this is that you've got to sort of plan for worst case scenario also. So in this case, this collar right here is going to have an equivalent length of 75 feet. All right, the master bedroom, that one only has 2 that follows it. So that's only going to have 60 feet. And then finally, these guys at the end, they have 0 following them. They're going to be 50 feet. And so you're going to put these in the speed sheet. All right. If you've got reducing trunk takeoff fittings, that is something else you can do here. If you know, a lot of houses, I guess, with basements where you've got in between the floors, you've got these funky fittings right here. Manual D has numbers for that too. Then you arrive at the boot, and the boot, for example, a straight boot has an equivalent length of 10 feet. Okay, but a 90 degree or an offset boot, 90 degree has 80 feet of equivalent length, and offset boot has 50. So you've got to think about that when you're putting boots on. Now, one thing that I forgot to change on here is, yes, we're using straight boots, but we're also going to have a 90 coming off of it. So that's just a mistake. We're just going to pretend that we don't need those. But realistically, when you're doing, if this is an attic system, which is what this is, an attic system, you're going to have a 90, or you're going to have to turn that flex down. So let's just pretend right now that we've got a really gradual turn and that we don't really need to put a 90 on there. But don't forget the 90s like I did developing this class. I promise you I put the 90s when I actually built this house, but I just didn't put it for this problem. But my point is, don't forget the 90s. In this case, we're just going to use this 10 feet right here. And then return air fitting. So the same thing here. We're just cutting in a collar, a round collar, into a return plenum. That's an equivalent length of 40 feet. We've got to put that here. And then the return air boot. A lot of times we just end up cutting a collar in a box and we stick a grill on that box. So that's an equivalent length of 30 feet. So Manual D has a chart with all these in there, and you're gonna put them where they go. And you're gonna do the same for all these other groups of fittings. There's return fittings and supply fittings. You're going to go through these. If you don't have that fitting, then you just leave it blank. If you do, then you find the right one and you put it in the appropriate spot. Total effective length. So we figured out how long our longest runs are, and we figured out how much effective length in feet that we have. Now we need to put them together. So the total effective length is our duct length plus all of our fittings. So not just our boots, but all of our fittings. We're going to put those together and find an effective length, which is sort of the simulated length that the air has to travel through. And so this is what our worksheet looks like so far. We've got, again, we have our duct lengths, our trunk, and our run out or our branch. We have all our fittings. And if you put them in this chart here, again, it's going to figure out which one is the highest. So now look what happened. Which one becomes the longest run? It's that dining room right there, that breakfast room. Well, wait a minute. That's not the farthest one from the unit. but it very well could be because we had other branches downstream. Now, if we do end up putting reducers in there, then yes, that would change, but we don't know that yet. So the point that I'm making is don't take it for granted that your farthest boot will always be your worst case scenario. Sometimes it's one in the middle. So if you're doing this worksheet right here and you've got a boot sort of in the middle of the house, a takeoff in the middle of the house that's got a long branch, go ahead and include it in one of those 4 possible worst case scenarios because it very well might be. And again, our return duct, we added not only our duct length, which is only 10 feet, but then our fittings, and we come up with 80 feet. So our air is simulated running 190 feet in the supply and 80 feet in the return. And so what a total effective length is when we add these two numbers together, and that's 270 feet. So that's the equivalent of having 270 feet of straight duct on our air handler. It's pretty surprising to see how much length, when you equivalent or effective length, when you actually do the math, that our air handler is fighting against. I also want you to understand something. Some of our longest lengths here, we had 35 feet and 20 feet. That's the straight lengths of ducts that we had. But look what some of these fittings make. You usually will have more length in fittings than you will an actual linear length of duct. That is not uncommon. That's actually the norm. So don't be surprised if when you add up all the lengths to your fittings, it is 2 to 3 times more than the actual length of your ducts. That is normal. Okay, the next step is friction rate. So you and I were both taught to immediately take our duct wheel out and set it to 0.1 inch friction rate. We just went through this whole process to arrive at the right friction rate right here. So friction rate, the calculation for that is we take our available static pressure. We've already calculated that. We multiply it by 100 and we divide it by our total equivalent length at 270 that we just figured out. So again, our available static pressure, remember we started out with 0.5, then we had 0.34 in component losses. We came up with 0.16 of available static pressure. That's what goes here. Then we multiply it by 100. This is what it looks like, 0.16 times 100 divided by 270. Everybody understand how we got these numbers here? If you don't, that's totally fine. Please speak up. We'll make sure you do. Okay. So we've got, this is our formula to figure out what our friction rate. So when we do the math here, we come up with a friction rate of 0.06. Wait a minute, that's, we were setting our friction rate at 0.1. Is there a big difference between 0.1 and 0.06? Let's find out. The Manual D worksheet does all the math for you. You don't even have to remember that formula that I just gave you for friction rate. Just enter everything here. It gives you the math. All right. And it comes up with a 0.06 friction rate. All right. So sometimes you're going to have 0.1. Sometimes you're not. You want to do the math. If the friction rate is below 0.02, the note says the fan may not deliver the required CFM. You want to increase the blower speed. You need more fan because you get too much ductwork, is what it's saying. If the friction rate is above 0.18, you actually have too much fan for the amount of ductwork you need. You're probably going to need some dampers to create some friction. Updated Manual D changes these numbers. It actually becomes 0.06 and 0.16. The speed sheet is a very old document. I don't know why they haven't updated it, but this is sort of the old thinking. The new thinking kind of tightens this up where we don't want to be below 0.06, and we're right on the bubble right here. And we don't want to be above 0.16. All right, so our target friction rate, this is what we're going to set our duct calculator to, is this number here. The range that is safe is 0.06 to 0.16. Here's what gets a little confusing, all right? A higher friction rate. So if we're more on this side over here, a higher friction rate, that means you have less duct resistance. So higher friction rate means less friction. That I know that does not make sense, and I'll explain to you why. A lower friction rate means you have more duct resistance or more friction. You may think, well, wait a minute, isn't friction rate of friction? So if I have a higher friction rate, shouldn't that mean my ductwork is more resistive? No. And I looked around for a good explanation of why this is the case, and the best one that I found actually comes from Dr. Allison Bales with Energy Vanguard. And he just does it perfectly. When you calculate the friction rate for a particular design, you're finding out how much pressure drop, here's the important part, you can get away with for each 100 feet of effective length of your duct system. If the number is higher, you can get away with smaller, more restrictive ducts. If the number is lower, you have to use larger ducts. Think of it in terms of pressure drop allowed, and it makes more sense. So what he's saying is that a higher friction rate means that we have more pressure drop allowed. We can get away with smaller ducts. We have a lower friction rate, we have less to work with. So I know that's a little bit backwards thinking, but that's the explanation why. All right, so we have finally arrived at our friction rate, and now it's time to size our ducts. All right, let's go back to that rule of thumb. Everyone was taught to set your friction rate to 0.1 on your duct calculator, but our calculation here told us 0.06. Let's see if it actually makes a difference. In both cases, our flow rate in our sample problem is 1200 CFMs. All right. Look what the difference in duct size is between the rule of thumb and what the actual calculation is. Now, everybody knows that you can't use 14-inch duct. You can't go smaller. You have to go bigger. And the next size up is 16. So we're going to have to use 16-inch here. And we're going to have to use 18-inch here. So we're going to have to round up to 16 here or round up to 18-inch there. So the 0.1 friction rate, if you just use a rule of thumb, you probably were going to use 16-inch. But you actually, if you use 16-inch, you won't move enough airflow for this duct layout. You'd have to step up to 18-inch for this. So it's really important to do the math, because that difference in duct size right there could be the difference between you moving 1200 CFM or 1000 CFM having comfort problems. The very next step is check velocity. So after we figured out what our duct size is, putting in the friction rate that we calculated, we got to do a duct velocity check. And velocity is very important when it comes to residential ductwork, because velocity equals noise. And again, that's one of our goals when we design duct. We want to design ducts for quiet operation. So Manual D gives us some guidance here. It tells us what our velocity, and we measure velocity in feet per minute. All right, so don't get that confused with cubic feet per minute. That's air volume. Velocity is feet per minute. That's speed. It's just like miles per hour. It's a unit of time unit of distance per unit of time. So miles per hour or feet per minute. Velocity. The faster the the air screens through that ducts, the more noise they're going to make. So it's given us some guidance here. And these are some relationships that we can sort of think about. If we increase our duct size, yes, we will move more air through that duct. That makes sense, right? If we decrease our duct size, yes, we're going to move less air through that duct usually. If we increase our duct size, our velocity goes down because the air has sort of more places to go. It can go side to side and not so much down the duct where we want it to go. If we decrease our duct size, our velocity, the speed of the air, goes up. So if we increase our velocity, our noise goes up. All right. The faster an airplane flies through the air, the more noise it makes, right? If we decrease our velocity, we decrease our noise. So it can be said that if we decrease our duct size, our noise goes up. If we increase our duct size, our noise goes down. And so Manual D is saying that we've got limits of how much velocity we can allow to run through the ductwork. And if we exceed those limits, then we need to increase the size of our ducts so that our velocity goes down. And when our velocity goes down, our noise goes down. So here's what it tells you. It says conservative, they'd like for you to be in this area, but this is where you need to start making some hard choices. If we exceed 900 CFMs in either rigid or flex duct, they say we need to go up in duct size. Okay, so if velocity exceeds the max, we need to upsize the duct. So whenever you size your ducts, you always have to remember to check the velocity. In fact, when I used to use one of those duct wheels, I literally wrote on it with an ink pen, check velocity, as a reminder every time I did it. So when we apply 1200 CFMs here to an 18-inch duct, our velocity is below 900. Good deal. Our supply duct is under 900 feet per minute. Does rigid mean ductboard or sheet metal? It means sheet metal. And they don't really give you a chart for ductboard, but as we can see, 900 was for both of them. That was a question in the chat. Okay, so in this case, we started out with 16.49. Of course, we had to round it up to 18-inch. We round up to 18-inch and we plug in 1200. Our velocity is below 900, so we're good to go. All right, so our trunk our supply trunk, blue is supply, red is return. It's just like the field piece job link stuff. The blue is supply, the red is return. 18-inch comes off the unit. Well, then when we come off the unit, we start branching off. And what's left in the trunk is less airflow. So at some point in time, we can actually go down in size. But when do we place those reducers in there? Well, what we want to do is check our friction rate. Every time we pull a takeoff off of this trunk, we want to check our friction rate. And the friction rate should get better. But if we decide to go down in size, we cannot exceed our friction rate that we already established as 0.06. So if we exceed it, we have to stay with the bigger duct. If we can go down in size and we don't exceed our friction rate, then we're good to go. And so we start, every time we take off a branch, we check to see how much airflow is left. And we try to see, can we reduce our ductwork down to 14-inch yet? When we do the math here, it doesn't work for these branches. 27 right here, 114 is this one. And let's see, 47, it doesn't work for this one. All right, finally, when we get to after we remove this much air, we're at this point in our duct, the airflow that's left out of that 1200, well, now we can get away with 0.14. All the other times when we tried to plug in 0.14 here, we got a friction rate higher than 0.06, and we're not allowed to do that. All right, so we've got something in the chat here. Oh, gotcha. Okay, so finally we can reduce to 14-inch after this takeoff here. And we're just going to repeat that process all the way down the trunk line. I'm not going to waste y'all's time doing that, but that's the process, is that after we take off air from the trunk, we see how much airflow is left, and we check to see whether we can go down a size. If we can't, if this number exceeds our target friction rate, then we have to stay the same size until we take off the next branch. Sizing the return duct, same story here. We've got one big return, but how big should it be? Well, we've determined that it needs to be, let's see, I think it said 16, but we want to check the velocity. Here's the point that I'm making. Manual D gives you those limits for velocity, but notice on the return side, we're not allowed as much as 900 anymore. Now we're only allowed 700. So again, if we find out that our ductwork exceeds the max, we got to upsize the duct. So we're going to check on it. This is our return side. Okay. We plugged in 0.06, and not only do we can't get 16.49-inch ducts, but also, even if we could, that velocity would exceed 700. So it's just another reason why we have to bump that return back up to 18-inch. And now at that point, when we plug in 18-inch, 1200 CFMs, it tells us our velocity is below 700. So we're going to have an 18-inch return trunk. A few other considerations, and we're going to take a break. This pantry, 51 CFMs. You don't want to ignore pantries, especially in cooling climates, because people want to sort of keep their food cool. But just remember, in the wintertime, you're going to be dumping 51 CFMs of hot air on there. And so sometimes it makes sense to put some kind of damper or something in that pantry so that the owners can throttle that air back without having to go up in the attic and do it. The other thing is 51 CFMs at 0.06 friction rate is a 5-inch duct. Some of you guys work with 5-inch, 7-inch, 9-inch ductwork. If I go to a supply house here in North Carolina and I ask for 5-inch duct, they're going to look at me funny. So sometimes you got to bump it up to a 6-inch duct because you can't get that size. So that's another reason why you may bump up duct size. Another thing is this is the master bedroom. We've got one run at 180 CFM. That's an 8-inch run right there when you do the math and you plug in the friction rate. Sometimes it makes better sense in a large room to split this up into 2 branches. Because you want these people to be comfortable. And maybe if you have 180 CFMs coming out of one boot, they may feel it at night. These are the people that paid your bill. Make them happy. Sometimes it makes sense to split this up into 2 6-inch runs. That's just some of the considerations you want to think about. All right. What if your friction rate is less than 0.06, which means what if your ducts are too restrictive? What are your options? Well, you can select more efficient duct fittings with lower equivalent lengths. So remember, we drilled a hole in the side of our plenum and we just put a side tap on there. We could have used a squared around. That would have gotten our effective length down. We can use shorter run out lengths. So maybe we don't have to go all the way to the perimeter of the house. That is sort of old school mentality in old houses with single pane windows and no insulation in the walls. We had to wash that wall with heat. Now every house is insulation. Every house, that new house, is going to have double pane windows. We can actually get away with putting in supply registers on the interior of the rooms. You may want to consider moving the air handler to a central location so you don't have to go across the entire length of a house. If you're working on a ranch house, it may make sense to put the air handler in the middle of the house instead of on the end. You may have to do things like find a coil that has less pressure drop on it. You may have to upsize your media filter so that you get a lower pressure drop on it. Maybe choose grills and registers with ones that have a lower pressure drop. So these are all little tricks that you can do to get these numbers down so that your friction rate is a little bit more manageable. And finally, consider a higher target static pressure to begin with. So remember, we chose 0.5 because it works really well. But you may have to bump this up to 0.6, maybe even 0.7 in order to get all these numbers to work. I wouldn't start off that way, but you may have to do that. When you get above 0.7, you start having problems, and we'll talk about that in a later slide. And as a last resort, increase equipment size for a stronger blower. Nobody likes to put in bigger equipment. And I'm not saying bump this up from a 3-ton to a 4-ton. I'm saying try to find an AHR matchup with a 3.5 or 4-ton air handler for a 3-ton condensing unit, just so you get a bigger blower in that air handler that maybe has a little more horsepower. I tell you what, let's take a break and then we'll talk about a couple other considerations. Let's take a 10-minute break. What time is it? It is 7:10. So let's come back at 7:25 and we will continue on.
I may be late, Tim. I got to go get some ice cream.
Hey, Tim,
Yeah.
you fielding questions during the break?
Yeah.
All right. So Bruce is asking, is there a correlation? And I really don't know the answer. In Louisiana, we fight with 125, 130 degree attics, which is a considerable amount of heat gain in the duct system. In fact, when we do a manual J, you often notice that your largest heat gain is from your ductwork. So we know that we fight that. Is there a correlation between friction rate and capacity or delta loss in an attic on long runs?
I
Or
think,
is it strictly heat gain?
well, friction, as far as the air having friction through the ducts, that the only place where we would add that to our manual J is actually the wattage of the motor. And because the wattage of the motor is getting distributed through the friction of the air moving through the ducts. So let's say that the motor pulls 500 watts. That 500 watts is electrical energy that is converting to heat energy, because that is the amount of energy it takes to push the air through the walls of the duct. So it's kind of an interesting way to think about it. But as far as like duct velocity, if your duct velocity is super low, like really, really low, like if you decide to put 24-inch ducts on a 2-ton system, and your air is sort of just lollygagging down the trunk, it's going to pick up a little bit more heat. But it's not really something that we pay a lot of attention to. Like if you're running 500 feet per minute versus 900 feet per minute, you don't need to adjust your load calculation for that.
Right. And most manufacturers include blower heat already. The only one that I'm aware of that you have to account for that is Linux, I think. But I don't see, unless you had a really, really poor duct system, that a blower motor able to create enough heat energy to affect a delta downstream.
Right. Yeah, it's not something, and really, like even Manual J says it's like 1,700 BTUs. I mean, it's negligible.
Right.
And the heat gain is what you enter in through there. And I don't know how the latest Manual J does it by hand, but a lot of it was it's really talking about surface area, like how far away do you have a trunk and branch system, or is it a radial close to the unit? Of course, your R value is a consideration, that sort of things. But now I let the software do all that. When I taught a Manual J class, I had to like learn how to do it with the speed sheet all over again. It was like, oh God, like I learned this stuff like 15 years ago, and we have calculators for that now.
Yeah.
But in order to teach the concepts of it, I had to learn it all over again. And that's why I tell everybody, man, just get software. Like we're so far past the do it by hand. Understand the concepts so you can qualitatively diagnose things. But man, don't quantify anything by hand anymore. We got software for that. All right. Let's get started. Let's talk about case coil pressure drop, because if let's say we were putting, instead of a heat pump in this sample project, a furnace with a case coil, you can't just arbitrarily choose 0.1, 0.15, 0.2 for your case coil pressure drop. Your case coil is a component. We've got to factor that in our component losses. But as you can see from this chart, we've got pressure drops that range from 0.08 all the way down to, good grief, I see 0.47 right through here. I mean, that's huge. So you need to be able to look it up what your case coil is. So you've selected your equipment already with Manual S. Now you're doing Manual D. You're figuring out what your component loss is. Don't assume. I've gotten in trouble doing this before. So in this sample problem, let's say instead of a 3-ton heat pump, we're putting in a 3-ton air conditioner with a comparable furnace. All right, so our CFMs are still 1,200. And here are the 3-ton coils that we're dealing with. 3617, that's a 17-inch cabinet. 3621, it's a 21-inch cabinet. Then we have a 3721 and a 3817. Oh, sorry, share my screen. Thank you. Okay. I was seeing it. All right, thanks for doing that. So yeah, here's our coil, case coil, pressure drop. Every manufacturer should give this to you. Notice this one is for a wet coil. That's because wet coils have more pressure drop on them. So in air conditioning, when you've got a wet coil, you're going to have more of a pressure drop than you would have as a dry coil. So pay attention to that also. Some of them give you this chart for a wet coil. Some of them give you 2 charts. Some of them give you a multiplier. But just pay attention that you've got to do it for a wet coil if you're sizing this for cooling. So here we've got a 1,200 CFMs, and our coil is, these are some of the 3-ton coils we can choose from. Now, of course, we could choose a 3.5 ton coil and even a 4 ton coil, probably find a matchup for these. But just for the sake of this class, here's some of the coils that we've got to choose from. Look at that CV PVA 3617. It's got 0.29 inches of static on there. When we first started this problem, we were talking about component losses a little while back. I put 0.1. It's actually 0.3. That's a big target to miss. So don't assume that the case coil you're going to use has got 0.1. You want to do the math, look it up, and actually plug that number in. That's the point that I'm making here. Media filter pressure drop. Again, don't assume it's going to be one thing. Look it up. All right, this is Aprilair's pressure drop chart for some of their filter media. 1,200 CFMs. We got a 3 ton unit. Maybe we're tempted to use their 113 model. I think that's a 16 by 20 because we've got a coil or an air handler that kind of matches that physical size. Well, you don't match these filters according to what size air handler you have. That is a bad idea. Notice this one's got 0.29. So let's say that we had 0.29 on our case coil and 0.29 on our media filter. That's essentially 0.6 component losses. That's more than our static pressure was starting off. That's never going to work. So what I'm saying is look it up. And what you're going to find is, and I'll show you a chart that I created later, is that you're going to start leaving some of these smaller filters alone, and you're going to start playing in this range right here when we talk about media filters. All right, yeah, that's a 16 by 20. That's a 20 by 25. Look at the difference in static pressure drop across there. All right, well, this is where we're supposed to take our break, but we'll just we really need to kind of move on. We'll have time for questions here in a bit. Best and worst practices. Talk about reducers. We use reducers to save material costs. That's one reason. They also maintain a design friction rate and static pressure. When we don't use reducers, all our air sort of wants to come out of the first few ducts, and there's not a lot of air to come out of the last branch takeoff. So we sort of use reducers to maintain a design friction, a static pressure, a velocity in the ducts. But here's the point, and we were talking about this a little bit on brakes, on last break. There is no such thing as too low velocity in the trunk, within reason. All right? Velocity matters at the boot and the register because that's where the air needs to speed up and that's where it gets thrown out of the register. If it's kind of slow through here, no big deal. But when it comes out of the register, we need it to be at our design velocity. And that's what Manual T talks about. So again, we used to just design systems. If I knew I had a bunch of 6-inch runs, a few 8-inch runs like Good Supply House, give me 6 4x10 by 6s and give me 4 6x10 by 8s. And that's how I used to select my boots. That's worked sometimes. But really, the better way to do it is actually select your boot and your register using Manual T. That's a different class. But I'm just saying that velocity matters at the boot and register a lot more than it does at the trunk. It is important to maintain some kind of static pressure in the air so it goes where we want it. If we're trying to push air through, let's just make it an extreme case. Let's say we got a 2-ton air handler and we've got a 24-inch supply duct and we cut a bunch of takeoffs in that supply duct. Where is that air going to go? We don't know. It's sort of probably going to just fall out of the first few takeoffs because that's the path of least resistance. We're not building any pressure in that duct. So the velocity does matter. Duct size does matter. We want to avoid extremes, but that's the purpose of reducers. And a lot of people think it's, well, we have to maintain the right amount of velocity. That isn't the most important thing in the trunk. The velocity really matters at the boots. Not that the velocity doesn't matter, but a lot of times I was taught that it's for the velocity of the trunk, and that's not the most important reason. All right, so we're talking about air. This is what happens when you oversize duct. You don't have reducers in here. The air sort of just finds the first hole and it kind of falls out of it, and you don't get any kind of throw. And then a little bit of air goes to the next one, and there's not as much air for the last one. And maybe this is the room, the great room, the living room that has all the west facing glass. You need more air coming out of there. You're not going to get it unless you start throttling back some of the dampers here of these takeoffs and build some pressure back in the trunk to push that air farther down. All right, grills and registers. Manual D gives you some considerations here. They give you a maximum velocity for a return grill of 500. So do the math. If you have a 16 by 20, 16 by 25, you're trying to pull 1200 through it. And every grill has a certain amount of free area. Usually about 75% of this grill is actually free and 25% is made out of metal. When you do that math, you come up with, that doesn't seem right. I don't think that number is right. But anyway, do the math and you'll come, if you're over 500, you want to go bigger or you want to add another return so that less air gets pulled through it. If you're using the grill as a filter grill, you really want to slow that air down to around 300 feet per minute, or else the air gets shot through the filter so fast that the filter doesn't catch the dust. It's sort of like tossing a tennis ball at a chain link fence. The chain link fence is going to catch it just about all the time because you're just tossing it in there. But if you fired it out of a cannon, a few tennis balls are going to get through. And that's the same principle there. Avoid these nice little decorative registers that homeowners really love because they don't throw air. You want to get ones that actually have some louvers on there, that actually have some test data. And I'll be honest with you, the stamped $6 register that we get at the supply house, there's no test data on there. If you try to look it up, it's not there. But the commercial brands that make these registers, the better quality ones, the ones that cost about $20, $25 each, they've got test data, so you know actually what your air is doing. So again, we want to avoid those habits of just going to the supply house, give me the cheap grill, give me the cheap register, letting the homeowner bully you into just, well, I want to put my own decorative one in there. Those are not good habits. Those are not good practices. And I've been there. I'm not throwing shade. I didn't know any better either for a long time. Panned joists. That's where you take a floor joist and you screw some sheet metal on it. You make a box out of it. You return that to a return air opening. Avoid that, please. Pan joists leak a lot. I just worked on a beach house where that was that's part of the humidity problem in the house. So the pan joists were there and we were leaking beach air right to the air handler. And we're removing 80 gallons of water a day out of the house and the house is still humid. The humidity was coming from somewhere and it's getting sucked into the pan joist. Those are bad habits to be in. It's added to the code book, but a lot of municipalities or states, other municipalities put it back in the code book to use them. So again, not a good idea. Try to avoid them. I want to talk about elbows because elbows are huge. There are good elbows and there are bad elbows. These elbows are the swivel type. A 90 is about 30 feet and a 45 is about 10. So if you were to take two 45s, space them out and make a sort of a round 90, instead of just using 190 to make a turn, you'd actually save 10 feet of equivalent length. Square elbows. This is a big one, y'all. This is the worst square elbow you could possibly find, especially one that's not like square, it's more rectangular. These sharp edges right here especially the inner corner, but also the outside corner, these create turbulence and it causes restriction in air. Square elbows, if you have turning vanes in them, notice a big difference. This is the equivalent of 80 feet. You stick some turning vanes in there, it goes down to 10. Big difference because we're taking out that turbulence. These are even better. Now, we see rounded elbows, but a lot of times they're squared on the inner throat. That's actually more important. I'd rather have one with a rounded inner throat and a square outer heel than the other way around. But notice the difference here between this guy, which is 80 feet, and this guy right here, when it's a nice, easy turn, is 15 feet. Now, sometimes you don't have a choice but to put a square one in there because you got tight spaces. I get it. But just know you're paying for it. Okay. All right. Same thing here. You got these turning vanes in there. we can, if we are really running, if we're out of options and we've got to try to knock down some duct friction, these are the expensive duct fittings that we try to avoid, and sometimes we got to use them in extreme cases. But this is why we try to make the rest of the system more efficient so that we don't have to use these to get the airflow we need. All right, other important information here, supply trunk junction fittings, T fittings. Notice here, if you've got a branch, trunk line, a takeoff with a 90 on it, that's 100 feet. That's huge. That one little takeoff in a 90 is equivalent to 100 feet at 900 feet per minute of velocity. Another thing I want you to show you is T's. You want to try to avoid, and I know it's hard because the supply house doesn't stock good fittings typically. But again, if you got a system that you've really got to sharpen your pencil and get the friction down, T fittings are bad, Y fittings are better. There's a lot less resistance here with this Y fitting because you're sort of going in the direction of airflow. All right, returns, same thing. If you can get that return to kind of merge in with the trunk, it's a lot better than a T fitting. Okay, big difference in equivalent lengths. It's even more so on returns from what I understand. When you're trying to suck in air into a trunk and it's a T fitting, there's a lot of turbulence that goes on with that. So just keep that in mind. I know it's not easy to do Ys and to get fittings like that. And sometimes you don't really have to worry about it. You can get away with this, but sometimes you can't. This is where you can save on some friction. Again, I'm sort of kind of making a pictorial diagram of here's the flow of air. And when we try to bring in a return into a T, the air doesn't want to go in there. It's a lot of friction. It doesn't want to pull from this duct that much. Same thing with the supply or with a return. It's a lot easier if we just merge that air in there. All right, junction boxes that barf out a bunch of flex. We see that a lot. There are better ways to do it than others. All right, notice some of the rules here. A straight run approach and straight run departures with no turns in the duct runs near the junction box is better. Entrance and exits on the sides of the box, no top and bottom openings, and the radius of the turn is divided by the diameter of the duct. So we're saying if you must have a junction or box here with a bunch of flexes coming out of it, side tap it. Don't tap on the bottom and the top. The airflow needs to be a little bit more predictable. If you're going to pull flex, make the flex turn easy. That's what Manual D is telling you here. Notice here, we've got some other rules. We've got a junction box. And what they're telling us here, I think I've got it highlighted. We don't want to do something like this. Exit opening. So the exit openings, so if airflow is coming in through here, these are exit openings here. At least 2 diameters from the entrance. So I'm saying if we're got 12 inches here, then we want to have at least 24 inches of diameter before our first takeoff. So in other words, those little cubes that we see sometimes that just barf out flex, they're never going to work. You're never going to have 2 duct diameters before your first takeoff. They're not good ideas. The air goes in unpredictable ways. It creates a lot of turbulence. I've taken these out before in a job and replaced it with a trunk and branch system and knocked, 0.3, 0.4 inches off static pressure just doing that. All right, so what it's saying is if you've got, I'm sorry, it's not the diameter of the duct coming in, it's these diameters here. So if you got 6s coming off of here, you need to have twice that diameter before your first takeoff. All right, that's sort of the rules. This is in Manual D. Just review it if these are the duct systems that you're putting in. Just make sure you're doing it right. All right, so our Manual D review before we get into some duct diagnosis. Good duct design delivers our air quietly, efficiently, quietly, economically, accurately, comfortably. Our duct design steps, we're going to select a total external static pressure that we'd like the unit to run. Then we're going to figure out our component losses, our coils, our grills, our registers, our available static pressure. It's what's left. We design our ductwork for that. We've got to quantify our total equivalent length or total effective length. That's our duct straight runs plus our fittings. Only then do we know our friction rate. We size our duct to friction rate, but then we still have to go back and make sure our velocity is within the limits that Manual D gives us. Let's talk about best practices or worst practices. Best practices is single versus multiple returns. This is more regional. You know, some places that's what they do. They use a single return. Other places you got to return every single bedroom, every single room. Let's talk about some of the pros and cons. All right, single main return close to the air handler is usually recommended, and here's why. It's a shorter return. You're not snaking returns all through the house. You've got less ductwork to pull through, so you're going to have lower TEL. You're going to have better friction rates. Room-to-room pressure imbalances, though, have to be addressed. That's a problem. When you don't put a return in every room, then you may have room-to-room pressure imbalances. So let's put an example. Let's say this is my air handler. This is my central return. That's the only return in the house. What's going to happen when these doors close at night and the unit turns on? The units, every room has at least one supply in it. So these rooms with the door closed are going to go into a strong positive. This bathroom probably only has a 4-inch. It's probably going to go into a slight positive. The owner suite or the master suite, when this door closes, you've got a couple of supplies here. You've got one here. You've got 1 or 2 here. You got all these supplies that are behind this door. This is going to go into a heck of a positive pressure. The rest of the house, you're pulling all your return from the middle of the house, but you're not getting all your supplies back. So this house goes negative. It starts pulling in humidity and particulate matter and chemicals and dead rodents from the attic and all kinds of stuff because this is in a negative. So we have to do something about this situation. Yes, we have a nice short return. Our duct friction is really good. Our unit's happy. Our blower's happy. But we created other problems. So we got to deal with them. So multiple returns, this is another option, allows for a almost neutral room pressure if we size them correctly. Or we can use jumper ducts to provide a return path back to the return. So I love jumper ducts. Here's multiple returns right here. So here's our air handler. We run a return here. We've got a return in each bedroom. We've got one all the way down here to the master suite. We better size that one correctly because our air is going to want to come through here. And just because you put a return in this room doesn't mean it's going to pull enough air. So that is another problem with return. Plus, we've got to add all this effective length to our duct calculation. So yes, it does help with room pressurization, but then we may have duct length problems. So that's the problem with multiple returns. Again, you can do it, you just got to deal with it. Or you can use jumper ducts to provide a return path to the main return. So in this case, I got a little smarter with my duct design. I put my air handler a little bit closer in the attic to, this more mimics what I actually did in my house. I got the unit here because that's where the platform ended up being. I got a return going to the owner's suite because there is a lot of air that has to get out of that room. But instead of running return all the way over here, what you could do is just put some jumper ducts so that you create a return path back. So you sort of get the best of both worlds. You get a short return, which helps with your duct sizing, but you also get that return path. And it's really easy to do. You either put a transfer grill or jumper ducts. These are really cheap. You don't have to buy a big trunk that goes all the way down here. So it sort of checks all the boxes. That's why I like using it. So that is something I really want y'all to consider is running short returns with jumper ducts. Now I don't suggest using jumper ducts for the master suite just because when that door closes, you've got 3 or 4 rooms that are behind it. And as you're going to see in a future slide, that's too much air for a jumper duct to move. Here's the slide I'm talking about. This is what a jumper duct does. You got a bedroom, and like the main part of the house that's open that communicates with the main return. Your air is going to have a path to get out of that bedroom, but you got to size them correctly. Let's say you got a bedroom with 75 CFM supply. All right. You feed it with a 6-inch supply duct. You may think, all right, cut in a 6-inch jumper. Wrong. Jumper duct diameter, in order for that air to find its way out of that room, you got to upsize that thing up to a 10-inch. So the only way you can get this maybe down to 8-inch is if you have less airflow, or maybe you put a little undercut in the door so that some of that air escapes the room that way. But if you have a no undercut in the door, what this guide is telling you is if you're putting in 75 CFM in that room, you need to have a 10-inch jumper duct. So a lot of people don't realize how big the jumper ducts and what the registers that correspond to that need to be. So what I suggest to you is, don't oversize your unit. So you only put in 75 CFMs because that's what the room needs. Try to get a little duct or door undercut if you can work with your builder on that, so that this can maybe go down to an 8-inch. And an 8-inch jumper is a lot more manageable than a 6-inch. But I would never put in a 6-inch jumper with a 6-inch supply unless I knew that these numbers worked out good. That's just what I've learned over the years. You want to avoid a pressurization in a bedroom. Anything over 3 pascals is too much. Excuse me. All right. Flex duct. We have a lot of flex duct in this area. I know we got people from Louisiana down here in the South. We love some flex duct. Problem is, a lot of us suck at putting flex duct in. So they did a study to see, okay, well, if you actually installed flex duct the way it's supposed to be installed, how does it perform? What they found was straight, tight flex performs almost identical to hard pipe. So what they've got here is this graph, and actually there's 2 lines. They look like one line, but if you look really closely, there's 2 lines. One of them is rigid sheet metal, the other one is a flex that's actually been stretched. And as we can see, they perform almost identical. The problem is when you let them sag or compress it with just a little bit, these numbers start separating, okay? And the performance of duct sharply falls off very quickly. So a 1-to-1 radius to diameter 90-degree turn with a flex. If you're going to turn flex, it needs to be a very wide turn. All right. And that's still going to take at least 20 feet of straight duct. It's going to be the equivalent of 20 feet of straight duct if you make a very, it's not going to take 20 feet of duct to make it, but it's the equivalent of 20 feet of straight duct. A 4% compression can mean a 40% reduction in airflow. So craftsmanship matters when you're running flex. Typically, I'm using metal 90s when I run flex, and then my flex is always straight and tight. All right, just kind of notice the difference here between it's stretched properly and just 4% compression. Dampers. Again, Manual D is sizing our ductwork for the worst case scenario, which means all the other ducts are probably going to be a little oversized. Or sometimes you need a 5-inch duct, and supply house doesn't carry a 5-inch duct, so you got to step it up to a 6-inch duct. So dampers create necessary friction to help you balance your airflow. So you always want to put dampers in branch takeoffs as long as they're accessible. If 2 trunks split, you may want to consider putting a damper at the split just so you can do some balancing there. Just remember to add that damper. You're going to have an additional damper, additional 0.03 to your component loss. Avoid dampering at the register because it makes that whistle, that noise. We want to avoid doing that. Whoops. At times, dampers may be needed to balance multiple returns so rooms don't go negative. We don't like to put dampers in returns. That's why I say put a central return in the house close to the unit, use jumper ducts. You don't have to worry about an imbalance of return to supply. All right, best practices, media filters and return drops. Everybody knows who Jeff DEM is. I don't know if you guys follow him on Instagram. One of the best installers I've ever seen. I mean, some clean work here. I mean, I wish they were all like this, right? This is the unit he took out. This is the unit he put in. Let's talk about media filters. Now, this isn't perfect. He's got a square inner throat here. I've talked to him about it. He says that their duct guy that comes before them and sells the jobs, that's just what he does. That's not Jeff that does that. He has to put in what they give him. But notice here the old duct, really skinny drop. That square 90 goes in the side of the unit. It's undersized, right? If you were to put in a return media filter that just matched that size of duct, it'd be way too small. What they did is they upsized it. They did use they made some attempts they upsize this. It looks great. They got at least a rounded 90 here. And notice they're splitting the return. They're pulling some of it through the side, some through the bottom. They got a nice big filter. That's kind of what you want. With a heat pump, you can do the same thing. Notice they upsize their ducts. They got a nice big drop. If for the life of me, I do not understand why years ago they have a giant return duct and then they got this little skinny jeans little return drop here. I mean, there is so much static pressure that you can relieve the unit of if you just change this thing out. So those are best practices. Use a big drop, upsize for media filter. This came from Nate Adams. He is also a proponent of a big drop. All right, let's talk about media filters and return drops. We talked about how we should look up the numbers. This is a chart that I came up with when I was selling a lot of media filters in my jobs. I wanted a quick reference that I knew that some media filters will never work on certain tonnage of units. So this is Aprilaire. This is just their MERV 11, their 1000 series. I created a chart. And not only was I looking for pressure drop, but I was also looking for velocity. And I wanted to keep my pressure drop and my velocity low. So green is good. Orange is okay. Maybe that'll work, and you want to stay out of the red. And the point that I'm making is here, try to select a filter with under 0.15 inches of pressure drop, because that's going to give you something to work with for the rest of your duct system. Under 300 feet per minute is desirable for a filter, because under 300 feet per minute, it can actually catch. A MERV 11 is actually a MERV 11 at 300 feet per minute. Most manufacturers will publish what that MERV 11, what velocity that is rated at. Over 500 feet per minute, and the MERV rating drastically goes down. It's sort of like firing a tennis ball into a chain link fence with a potato gun. Some of them are going to get through. Versus under 300 feet per minute, it's sort of like tossing that tennis ball through the fence. So here's an example, 3.5 ton unit. Which filter am I going to put in? Well, I've seen a lot of 3.5 ton air handlers with a 20 by 20 on them, butted right up to the air handler because it fits. It's a 21-inch cabinet, 20 by 20 on a 3.5 ton air handler. But notice that velocity is way over 500 feet per minute. So you sold them a MERV 11, but they ain't getting MERV 11 out of it. No, I would much rather go with that big 31 by 28. Now I got a nice low pressure drop. I got a nice low velocity. Or maybe they got 2 return ducts feeding into that return plenum. Maybe even give them 2 media filters. But pay attention to this stuff. Last thing you want to do is sell them a MERV 11 or a MERV 13, and they're not getting that performance out of there. You've ripped them off, essentially. 80 to 90% furnace requirements. All right, this is another big one. We're swapping out an old furnace with a new furnace. We're swapping out an 80% to a 90 plus. All right, there's a little bit of math here. Bear with me. Let's say the old furnace was 100,000. The new furnace is 100,000. The old output's an 80% furnace. You're getting 80,000 BTUs out of it. The new furnace is a 93,000 BTU output. Okay, so we're picking up a bunch of BTUs. This old furnace was probably oversized to begin with, and now it's really oversized. The old temperature rise was 40 to 70 degrees, and what we're trying to shoot for is a supply temperature rise somewhere in the middle. So in this case, the middle of 40 and 70 is 55. But notice that the new furnace, the temperature rise is a lot less. So that one, the midpoint is 45. All right. There is a formula so that you can figure out how many CFMs that you want to move in order to get 93,000 BTUs out of it versus 80,000. CFMs equals your BTU-H output divided by 1.08 times temperature rise. This is pretty much an inverted sensible heat formula. Here's the point that I'm making. The old furnace, when it was putting out 80,000 CFMs, 80,000 BTUs, it needed 1,346 CFMs to do the job. The new furnace, when you plug in our new BTU-H output plus our temperature rise of 45 times 1.8, when you do the math, all of a sudden our new furnace needs to move 1,900 CFMs. You're not going to get 1900 CFMs out of a little skinny jeans duct drop. You probably weren't getting 1300 before, but you're darn sure not going to get 1900 out of it. So as we are swapping out furnaces from an 80% to a 90%, good for you for selling the higher efficiency one. Great. But consider going down in size. Do your load calculation. Don't just say, well, I'm ripping out 100,000. I need to put another 100,000 back in. Do the load calc, because probably you don't need 93,000 BTUs output. And that way you can get away with less airflow. All right. So the point that I'm making here is if you just rip it out like for like, go with the higher BTU furnace, you're not going to be able to move the air you need through that little duct job. So you need to start looking at your duct work also. Size your units correctly, but also look at duct work. That's the point that's one of like the most important slides in this whole presentation. So the new furnace needs to move more air, but it's not going to be able to because of that little skinny jeans duct drop. All right, here's another important one. There's a lot of math here. Again, you guys are getting a recording of this. So feel free to pause it and take a screenshot of it during the recording. There are fan laws, and the fan law number 2 is about a relationship between CFM airflow and static pressure. And we're going to apply fan law number 2. We're going to apply a little bit of math to a problem. Our old unit moves 1,000 CFMs at 0.6 static pressure. So the unit was functional when we sold the job. We tested it. We determined it moves 1,000 CFMs and the static pressure is 0.6. Our new unit, when we do the load calculation, manual J, manual S, we determined, okay, we need to get 1,200 CFMs out of this. What would be our new static pressure, and will it work? Here's the formula. Our new static pressure equals our old static pressure times, and we sort of have to divide new CFM by old CFM first, square it. Here's our formula here. So we put in the numbers. 0.6 was our old static pressure. 1,200 is our new CFMs. 1,000 is our old CFMs. We got to square it. We do the math. Our new static pressure, when we put in that new unit, moving 1,200 CFMs, it's going to be 0.86. That's what it's going to need to overcome is 0.86 water column. So that's our new static pressure. Does our unit have the capability of doing that? Well, you got to look it up. So let's say we're going to go back with this 36060 model furnace. 0.86 is pretty close to 0.9. At 0.9 static pressure, there is not a dip switch setting here that gets you anywhere close to 1,200 CFMs. Okay, so what do you got to do? Well, I don't want a system that runs 0.9 static pressure. I probably, when I sell this unit, I need to sell some ductwork too. Or maybe I need to bump up to a larger size unit, but I don't like doing that. I'd much rather give them the duct system that should have been there to begin with. That's the point that I'm trying to make. You can actually calculate or estimate what your new static pressure would be by using fan law number 2, this formula right here. So this is kind of an important slide. So the new furnace cannot make 1,200 CFMs at 0.9. That furnace will never do it. All right, ducts closest to the air handler. If you're going to make any modifications to your ductwork without replacing the whole thing, the closer you are to the air handler, the more effect it'll have on the system, because that's where all the air is coming through there, and that's where all the pressure is. That's where all the velocity is, okay? As you get farther and farther away from the unit, you're going to have less of an effect on the total static pressure of the system. So change out your skinny jeans duct drops. Get rid of this stuff. Put some hard 90s in there. So if you're going to sell this system, don't just sell a new plenum to fit the new system. Put some ductwork in there. Those are just good practices. Put some 90s in there. Put a new return drop in there. But at the end, you cannot polish a turd. A bad duct system is a bad duct system. All right, maybe you can make a few modifications. Maybe you can't access all the ducts that you really want to access. You got to sort of just make some repairs. But it's a lot easier just to rip it out, put it in, because again, you touch it, you own it. So if you're going to touch it, make sure you can own the job. A poor duct system rarely can be fixed. The best way you can guarantee results is to go back with the properly designed system. Now you can start all over. You can start with the manual J, the manual S, the manual D. You're not trying to fix something that's already there. It's really hard to apply manual D to an existing system. Manual D is really for new designs. Talk about measuring airflow and duct systems and duct static. I think that was supposed to say duct static. Here are some of the tools that maybe you've seen before, maybe some of them you haven't seen before. The first thing, we're going to talk about duct diagnosis. This is the part of the class where we're talking about duct diagnosis. First thing you can do is do a visual inspection. Everybody knows this thing sucks, right? This duct system sucks. You don't need a flow hood to tell a customer this duct system sucks, all right? You probably don't need any kind of tools to tell them that this duct drop sucks. Probably don't need any tools to tell them that this flex trunk snaking all over the place is bad. All right. So some of the things you want to look for on every single job you go on, including jobs that you've put in yourself. Okay. There's nothing wrong with realizing that maybe you wish you knew back then what you know now. There's nothing wrong with that. But every job you look at the ductwork. You're looking for things like long flex branches. So instead of running a trunk out to the closer to the rooms, they just pulled a bunch of flex from a box. You're looking for stuff like that. You're looking for kinked flex. See plenty of it here. Restricted trunks. See plenty of that there. Skinny returns. You're looking for those sort of things. These are opportunities for you to sell ductwork. Okay. Let's talk about some of the tools that we're going to use for diagnosing duct systems and being able. Okay, so we've visually inspected a duct system. We realize, yeah, it sucks, but I need to kind of show the customers some numbers so that they believe me. So some of the tools you want to use are things like manometers. Now, not all manometers are created equal. This is one that you see in every single supply house, and it's good for static pressure, like rough static pressure numbers. It's good for measuring gas pressure. I mean, everybody should have one of these on the trucks. But just because it has 3 numbers after the decimal point doesn't mean that it reads it accurately. A lot of these things become random number generators. And so don't think that just because it's got a bunch of numbers here that's actually accurate at reading. So again, you can use these for what you need to, but don't expect any degree of precision out of them. I love the JobLink stuff. I use MeasureQuick all the time. These static pressure probes are actually pretty good. So these are a little bit of an upgrade. I like them. This is one of the best bang for the buck manometers out there. It's the DG8 from TEC, and Chris will get a chance to talk to you about it. It's called a micromanometer because it actually can read those really small pressures that this guy can't. Even though he'll throw a number at you, the number that this one throws at you is actually accurate. And so these are better for more accurate static pressure readings, room pressure. So you can take a hose, you can toss it under the door and read as if that room is going negative or positive. And then you can use it for blower door and duct leakage testing. It's that accurate. Okay, so everybody should have one of these on the truck. I really want people to start using smart probes and MeasureQuick. But you also should have one of these. Maybe you don't break it out. You certainly don't want to put it on a gas furnace. Well, maybe you do, but to me, I think it's a little overkill to read manifold pressure. But really, our goal is to kind of have all 3 eventually. Maybe not tomorrow, but all 3. Static pressure probe placement. This is really important. I went through way too long in my career before realizing the right and the wrong place to put static pressure probes. The return goes in the return plenum right before the unit. Okay, you want to put it in a place that is not going to have a lot of turbulence. Unfortunately, the way this is, you're probably going to have some turbulence in here. So this number may not still be accurate, unfortunately, but it is what it is, right? Your supply probe, is this where you go to read total external static pressure? I need somebody to unmute and say no. But how many people learned how to do it this way before you learned the better way? I know I was one of them. I work with people. This is how we read it. But this is the air handler. This is a component loss. We have to read we're pretty much reading what the air handler sees. Again, anything that didn't come shipped and installed in the air handler is a component loss. And so, first of all, you want to always zero your manometer before you read it, and even like in between uses, because for some reason these things like to drift. But no, you want to put it here. So what I tell people is get one of those small little unibits, so that you don't drill all the way through and get to the heat exchanger, and just drill kind of the side of the furnace and close to the coil, not in the coil, but still in the furnace. The heat exchanger is nowhere near around there, but get a step bit. That way you don't accidentally slip and get into the heat exchanger. And just that's where you take your static pressure for this unit here. And when you do that, let's say this unit was measuring 0.8 static. That's a little high, but I'm not surprised if this unit was reading 0.8 because of all the ductwork on it. Talk a little bit more about external static pressure. Before you take external static pressure, you want to make sure that the coil is, for example, like an air handler, where the coil is part of the air handler, you want to make sure that is clean. If it has a filter, you want to make sure that the filter is clean. And if the blower chart that you're comparing this against was with a filter installed or not installed, if it's with it not installed, you want to remove the filter. But then you're going to run your unit. You're going to get a negative and a positive. Your manometer is going to tell you your total static pressure. Again, we talked about the static pressure is pressure pushing against all the sides of the ducts. All right. Now, static pressure does not care whether you got more on the supply and less on the return. As long as the numbers add up to 0.5, your blower doesn't really care. Okay. You could have one that's a little bit more negative on the return and a little bit less on the supply. Again, it's still 0.5. The unit, that's all the unit cares about. All right. Troubleshooting static pressure. So let's say you're reading a negative 0.25 and a positive 0.25. That means you have just as much, your system is pretty balanced. Balance isn't always good. I actually prefer, less of a negative because I like shorter returns. So typically in a shorter return, you're not going to have a balanced system. So don't think that just because your system isn't 0.25 and 0.25 that there's something wrong with it. You just want to make sure these numbers aren't really high where your total static pressure is high. But again, our unit's running. Now, let's say that we've got only one. What this is symbolizing is now our system has more supply free area than return free area. So what do we expect to see? Well, we're going to have more of a suction on the return because all that air is only going through one opening instead of two openings. So we're going to have a higher negative static pressure than on the supply. Okay. And we may be reading a high static pressure just because it's really trying to pull through that one little hole. So if you see something that's really imbalanced and you have an airflow problem, which side of the system are you going to start scrutinizing a little bit more? You're probably going to scrutinize the side of the system that has a higher number. That's the side of the system where there's a bigger potential for some improvements. All right, so which side of the system has the strongest static pressure? It's this one. Estimate airflow with blower chart. So I don't know how many of us know how to read a blower chart. I'll just go through it really quick. Every installation manual should have a blower chart in it. I've never seen one that didn't have some kind of blower information on it. Find your model number. Read your total external static pressure. In this case is 0.6. And then different units display differently, but then for example, this one has got dip switches. So you're going to see what dip switches are actually turned on and off, and you use that line. And when it intersects, that's your CFMs. But that only works if your unit is clean, if your heat exchanger in the furnace is clean, if your blower wheel is clean, all right? And sometimes we can't see all that stuff. So an older unit, this may not be accurate, but it's the best we got. With a newer unit, brand new unit, usually you can get pretty close with a static pressure. All right, with a heat pump air handler, this is what it might look like. This is a X13 motor with different speed taps on it. 0.6 is your static pressure. You found your model number here. You figure out which speed tap is actually plugged in. And then you figure out which speed tap is actually plugged in. And then you figure out which speed tap is actually plugged in. And then you figure out which speed tap is actually plugged in. And then you figure out which speed tap is actually plugged in. And then you figure out which speed tap is actually plugged in. And then you figure out which speed tap is actually plugged in. And then you figure out which speed tap is actually plugged in. And then you figure out which speed tap is actually plugged in. And then you figure out which speed tap is actually plugged in. And then you figure out which speed tap is actually plugged in. And then you figure out which speed tap is actually plugged in. And then you figure out which speed tap is actually plugged in. And then you figure out which speed tap is actually plugged in. And then you figure out which speed tap is actually plugged in. And then you figure out which speed tap is actually plugged in. And then you figure out which speed tap is actually plugged in. And then you figure out which speed tap is actu This is your CFMs. So it's that easy. So at the very least, you guys can invest in a decent manometer, and when you start up a brand new piece of equipment that you know the coil's clean, the heat exchanger's clean, the blower wheel's clean, you can quantify your airflow and make some speed tap adjustments using this method here. I'm not asking you to go buy a flow hood today, but this is very easy and it's pretty accurate, especially on newer units. Older units, we can't trust it as much. And we'll get into that in a slide here in a minute. So what happens when we don't get enough airflow coming out of a unit? What are our choices? Well, one choice is to speed up the blower. All right, not going to spend a lot of time on this chart here because it gets, not everybody likes fan curves. But pretty much what we're saying is whenever we're turning on a blower, there is an intersection of our blower at a given speed, at a constant RPM. A blower will make a specific CFM when it sees a specific static pressure. So here's our static pressure. Here's our duct system. This is sort of a line that our duct system performs at. Here's a line that our fan performs at. If our fan is running at a constant RPM, where these two lines meet, this is what our airflow is. So if we're reading 0.3 static pressure, then we're going to see that we're going to be moving 1600 CFMs. Okay. But what if we need 1700 CFMs out of this unit? Well, we would have to speed up. We'd have to find another speed tap, put it on high speed. Here's what happens in the fan curve. We have to increase the RPM to increase the CFMs. So we have to speed up our fan. That makes sense, right? If we're going to speed up our fan, we're going to get more airflow out of it. Now that curve moves along this line, and now we have a new spot where these lines intersect. And now at 1700 CFMs, we're now making 0.35 static pressure. So I want you to understand that there is a penalty. When you speed up the fan, your static pressure goes up. So if your static pressure was already too high, when you speed up your fan, it's only going to get higher. So just know that when you do something to one, it affects the other. So sometimes that's what we have to do. In order to get more airflow out of the unit, we got to speed up the blower. But just know that when you do that, our static pressure goes up. Higher static pressure is a byproduct of that. Another option is we can reduce our duct friction. So we have a unit, maybe the unit's maxed out. Maybe it's on its highest fan, speed tap to begin with, and we got to get more air out of it. So what options do we have? Well, we can reduce duct friction. And what that looks like is that, again, the same thing. We're moving 1600 CFMs at 0.3 static pressure. All right, we need to get 1700 CFMs out of this unit. So we can't speed up the fan anymore. Maybe what we have to do is make our ductwork less restrictive. And so what ends up happening, in order to get 1700 CFMs out, we got to really make some moves on this ductwork. And now look what our new static pressure is. In order to make 1700 CFMs, when we reduce the static pressure, we had to reduce it all the way down to 0.15. So, but it does work. As I'm saying, that there is a relationship. When we make changes to static pressure, we're going to make changes to CFMs. If we're going to make changes to CFMs, static pressure changes. But another factor of this is what kind of motor we have in the unit. Permanent split capacitor motors are going away. But these things, their airflow drops off as the duct friction increases. So we all knew that airflow on these old PSC motors, when we had a restriction, our coil was dirty, our filter was dirty, our ductwork was too small, we knew that these fans could not move the air that we needed them to make. They're sort of like this sloth here. It moves at one speed. You put it on medium, you're getting one speed out of it. You're getting whatever, 1100 RPMs out of it. It does not care how much airflow you want. It's moving at 1100 RPMs. Whether it moves the amount of airflow you want or not, it's sort of like a DMV worker. You're getting one speed out of it, all right? And so they don't speed up to attempt to move more air. And so the results when we had airflow restrictions is we had poor comfort, The fan amps were lower. That's another way that we used to be able to figure out, especially on commercial systems, if we had low airflows, we put an amp clamp on the blower, lower refrigerant pressures and temperatures. We know what low airflow looks like with a PSC motor, okay? And we usually had, now once we actually remove the restriction, maybe we put another return in here. Now things got a lot better. Our total static pressure looks a lot better, and our actual CFMs went up from 1,000 to 1,200. So PSC motors, we knew that we could fix those airflow problems. We couldn't speed up the motor any more than its highest speed, so we had to fix the airflow problem if we were going to get more airflow out of it. Then ECM motors came out, and all the dimwits at the supply houses started telling us, man, this thing will fix bad ductwork. How many of y'all heard that? I know I did when they first came out. They do not fix bad duct design. Those idiots are lying to you. This is what happens. Our target CFM is 1,200. Our actual CFM is 1,000. We've got a lot of negative static pressure in our return. And so we're asking the unit we got dip switches set. I want 1,200 CFMs. The unit realizes it's not moving enough airflow, so it speeds up, okay, to try to move more airflow. But look what happens to our static pressure. Now, yes, we are making 1,200 CFMs. Great, good for you. But then our static pressure went to 0.8 because when you speed up the fan, the penalty, again, is more static pressure, okay? So they didn't fix the bad duct design. They just sucked more air through a really bad duct system. But so they will speed up more to try to move the air you're asking to do. And it will move 1,200 CFMs or die trying. Now, a lot of them have died trying. The result is it pulls higher amps, makes higher wattage, their power bill goes up. The motor itself gets hotter because it's working harder. And then the motor pops within 3 years. And then we go and we pop in a new motor and we say, man, Carrier makes a bunch of garbage. And then 6 months later, that motor pops, and we're getting mad at Carrier when really we never even put a manometer on this thing to figure out why this thing is having to run so fast. So ECM motors do not fix bad ductwork. The result when we ask it to move 1,200 CFMs, when we have a duct system that is restrictive, we don't have enough returns or whatever, is a higher static pressure. And also think about, if you're running a really high static pressure on the suction side here on your coil, what's that doing to your P-trap? It might even be sucking through your P-trap because your P-trap isn't deep enough to overcome that return static. So that is another problem with that. Then the unit has got a bunch of water laying up in the cabinet of the unit. Then the motor pulls it up into the ECM module. The ECM module pops. And then, we're custom Carrier when it really was just a bad duct design. Not to say that ECMs and that they don't make junk. People make junk units all the time, but I think a lot of failure of ECM motors gets attributed to, well, they don't make them like they used to when actually the ductwork was ignored. Static pressure mapping. Here's how you diagnose a system. Man, I love seeing these little plugs in here, which means that they were actually testing for static pressure. Look, they even put a little spacer between the coil and the furnace to be able to not only to ease the airflow so we're not blanking off part of the coil, but also gives us a place to test static pressure. If they made it a little bit bigger, they could have even put in a little inspection door so you can look at the heat exchanger. So maybe consider doing that if you have the room to do that with your furnace and coil installs. Static pressure mapping. This is where we're trying to see what the pressure drop is across different components. So let's say when we do total external static pressure, we measure one here. We can't be on this side of the filter. We got to be on the other side of the filter. So we might have to even drill a hole in the door of the unit to read it. In fact, if you take this door off, you wouldn't actually drill a hole here because that just gets you into another panel. You may have to drill a hole in the side of the unit, but you guys get the point. Let's say that when we read total external static pressure is 0.65. Well, if we were to take the pressure drop across a coil now, so we're reading the furnace, in the coil and coming out of the coil, we read 0.20. Well, okay, that's not too far out of whack. Always zero your manometer before you're taking a reading. Just a little reminder. Then we read it across the coil, and then we're reading a 0.25 pressure drop across the coil. So we had 0.20 on the filter, 0.25. We know we had 0.65 total. That means that the ductwork must be 0.20. And all that is kind of within normal range. But if you were to see something that was really, really wacky, you could say that you've got a dirty coil and go ahead and sell a coil cleaning without actually inspecting the coil, because you took a pressure drop across it and then you compared it to the chart. So again, these are good selling tools for you also to sell work that actually needs to be done. But there are limitations of static pressure diagnostics. For one, you've got to have clean everything. You're working on an older unit and you've got a blower wheel that looks like this, or even just a thin film of dust. That static pressure chart that comes with the installation manual did not account for that. And so it's going to be off. So it's going to be highly inaccurate if your unit is not perfectly clean. So working on older units, I wouldn't trust it that much. On newer units, yeah. It's dependent on straight runs for accuracy. So sure, this is a great place to read static pressure. This is a decent place, but you've got potential for turbulence. You know, a lot of times, especially units down here in the South, we just got a square box with the flex coming off of it. That's our return plenum. We got another square box with flex coming off of it. That's our supply plenum. There isn't a lot of straight line duct to take an accurate reading. So you may get a static pressure, but you don't know if it's accurate or not. So that's a limitation. Like this system right here, I don't know if I trust static pressure on here. There's no straight line of duct. I'd much rather cut a hole in this flex and stick a tube in there than trust my reading in this plenum, unfortunately. And then I'd have to do the same thing there. So there's limitations. There's another method of estimating airflow, and that's with temperature rise. So here we have a gas-fired unit. Most of us know about the temperature rise method. Let's say we had a 70-degree return. Our unit's been running for 15 minutes. It stabilizes out at 120 supply. We got a temperature rise of 50. But we got to clock the meter in order to figure out how much BTUs we're actually putting into the unit. That's the part a lot of people skip. But if you're going to use this method, it's not accurate unless you clock the meter. And like here in the South, I've clocked the meter once. Like, it's just not something we do. It's probably something we should do more often, but it's just not something we do. But if you're going to get any kind of accuracy, you got to clock the meter. And then you're going to see, you know, what the input is, 88,000 for this nameplate here. You know that your output is an 80% furnace. So you know that you're putting out 70,400 BTUs of output. You plug it into our formula here, and we arrive at 1303 CFM. So if this unit is running how we're running it, we can say that, well, it's moving 1303 CFM. That's one way of estimating airflow, and people have been doing that for a long time, and it works. Same thing you can do with a heat pump. You just got to put it in emergency heat. Here's again 70 coming in. Supply is 100, 30-degree temperature rise. Don't run the heat pump at the same time. You got to just put it in emergency heat. Then you have to read the amps and volts only from the heat strip. You can't include the fan amps on there. You plug it in the formula, you come up with 758 CFMs. So it's a pretty decent way of estimating airflow. The problem is it only works in heating mode. A lot of units have a different fan speed for cooling mode. And a lot of especially in southern climates, we're not dealing with airflow problems in heating mode. We're dealing with airflow problems in cooling mode. Clocking a gas meter is tedious. It also we have to know what the BTU content of natural gas is that day, because the gas company changes it. We can't just assume it's going to be 1,000. And so that's sometimes not practical. You're going to have some inaccuracies there. And there's no gas meter on an LP system. So if you're way out in the sticks and they got propane, you can't clock the gas meter. So there are some limitations with the temperature rise method there. I have not used it that much in my career, honestly. Then we have flow hoods. The problem is with a flow hood, a good one that you can actually trust costs well above $3,000. Even the powered flow hood, that's really, really good, but they have limitations. You can only read grills up to a certain size. They're difficult to read on small registers and large registers and grills. And if you're really low airflow coming out of a supply, first of all, you have to read all your supplies and add them together. And then they don't account for duct leakage because you're only reading what's coming out. You're not reading what's coming out of the unit. You're just reading what's coming out of the ducts. And a lot of them have been known to be inaccurate at low airflow numbers. So you paid over $3,000 for something that is not that accurate. So there's limitations there. So wouldn't it be nice if we had a tool, and I really hope that, Chris, you there? You're up, buddy. Wouldn't it be really nice if we had a tool that didn't suffer from those limitations? So I'm going to turn it over to Chris, and he's going to talk about said tool. I'm going to stop sharing my screen, and we're going to hear Chris out for a little bit.
So
Hang on, let me.
there's a couple things I've told Tim I was going to show the class tonight that most people have actually, unless you worked for TEC, you don't know about this yet. This is going to be some super secret information that will not be on the recording that's going to go out to everybody. So you're getting first
Another
hand.
reason why I didn't let anybody record it on their own, because we're going to edit this out for the recording. Top secret.
Correct.
Go ahead, Chris. Sorry.
Top secret stuff coming down the pipe. And let me pull it up and we'll talk about it. So just giving you guys a little taste of that. And then I was going to offer everybody who showed up to this class, if you're here in this class, I'm going to hand out a coupon code if you want to acquire this tool. So if you want to write this down, it's my initials, which is CH 2023. If you enter that code in our store, it'll get you 8% off and free shipping if you'd like to acquire one.
Awesome. Comment in chat. Is it lowercase? Is it case sensitive that?
I don't believe it's case sensitive.
Worst thing that can happen is it tells you it doesn't work, then you do the other thing.
Yeah, and you can always reach me if for some reason you were here and you wanted to get one and it didn't work. Just you send me an email. I'll square it away.
I'll put it in the chat here because a couple people are asking.
Cody, what you smiling about, man? You smiling because you like that feature because you've already got one of those tools.
Let me get on that beta test list.
Yeah.
I have a couple questions on the TrueFlow grid.
Yep.
Let's say like I put in some units, like some 5-ton units, larger systems with the Aprilaire 31 by 28
Yep.
filter. I guess in that case, would I just have to put if I'm pulling air through the bottom, I could just put one of the grids inside of the furnace instead of in the filter, because you probably don't make a track for that size.
Correct. Yeah. So we order the raw material for the adapter plates from a company. They send it to us. The widest it comes is 25 by 30. I've tried to talk to my boss, see if we could get bigger. We haven't been able to get bigger yet. So that's a bit of an issue, but it's what people do to answer your question. Yes, you can put it in the furnace. The only rules we have on the TrueFlow is there has to be no restrictions 6 inches upstream, nor 2 inches, or nor any restrictions 2 inches downstream of the device. So if if it's touching the blower wheel, that's going to be an issue, right? It needs to have like a 2-inch gap. You give me 2 inches, I'll hold the specs of the measurement. Yep. And if you're doing that, select the filter slot when you're doing it.
Yeah.
Do the workflow.
Does a duct transition to a bigger, because if you're putting it, I mean, that's what I'm teaching here. If I put it in a media filter, I'm going to be transitioning out to it and then back possibly to a smaller size. If you've got that transition in there, does that count as a duct restriction where you wouldn't want to use a media filter?
It would be super, super minimal, like that one piece of transitional duct. I wouldn't be concerned about that in the workflow. So just to let everybody know too, the So we do a correction factor for the flow. That's how we cancel out the restriction from the grid based against the filter. That pressure measurement that does the correction is the supply pressure measurement only. So as you're pressure mapping the system, all of the pressure measurements leading up to the supply pressure measurement are strictly for pressure. That's pressure mapping measurements only. That supply pressure measurement and the next one when the grid's in, that's the correction factor pressure measurements that we're using. So don't ever feel like if this probe's not in the perfect spot for this pressure matching that it's affecting the flow measurement, because it's not. And if you ever use the tool and you're in one of the other workflows don't ask you to pressure map. They're built for they're built in there for raters who only want flow. So they'll go in and use like the 310 method, and they'll, just stick the pressure probe in the supply plenum, take a measurement, swap the filter for the grid, take another pressure measurement with the flow, and get a report.
Now, there's some questions here. Website to purchase. It's not TrueTech Tools, right? You need to go on theenergyconservatory.com.
Correct. How about I do this? I will put a quick link in the chat. Give me one second. Energy. You can buy it from TrueTech Tools though.
Okay. Yep. And there's offer codes there too where
Yep.
you can get a similar discount, but
so let's talk about this too, because this one thing I've been arguing with my boss about is our website build. and it's a little funky and we're working on that. But I want to just kind of explain, if you do want to buy it, how does the purchasing kind of flow? So let me share that. So if you do want to get one, because this confuses people, because we have different types of people making flow measurements in the world. Like a lot of raters and weatherization communities, they have what's called our DG1000 gauge. That's this big fat gauge over here. So if they already have a gauge, they can buy the kit with no gauge because they already have their gauge, because this will work with a DG8 and a DG1000. So there's different ways to buy it. Some people have a training room and they only want one adapter plate because they've installed like 4 systems with 20 by 20 filters in their training room. So we've sold it that way quite a bit. So when the product originally came out, before I was at TEC, right when it was hitting the market, I came on board. They invented it with 8 adapter plates, 14 by 20 up to 24 by 24 with a cut to fit plate. They call it the standard kit. Within a first month, I said, well, that's got to change. I was like, because I need at least a 20 by 30 and a 24 by 30. I'm like, that is like mandatory for Louisiana. And so we have those 2 plates. So if you're somewhere in the country, you never see larger plates than 24 by 24, then a standard kit might be your best option. And if you don't have our gauges, this kit with the DG8 would be your best option. You have a gauge, basically as you go across, you'll see what's happening here. Standard kit with no gauge. But if you're someone who's like, man, I want to pick and choose my adapter plates and I don't have a gauge, this is for you. So what happens on this page is you'll click it with the DG8 and then you will make selections to the right. And as you make your selections, the price changes, right? And that's you adding your specific adapter plates you want to get, which you'll see we added the 24 by 30 and the 20 by 30 to that page. Has anybody got any questions about that, or it's not super straightforward. It could be better, but I'm just trying to make sure if anybody buys one, it's not confusing.
that's really helpful because I was trying to figure it out myself when I was.
Yeah, it could have been better for sure. We're working on it. So
Now,
many things. we could do
My
better.
question is, there's also like 14 by 25. So what would we do if we've got a 14 by 25 filter in the grill, no media filter? Like, would we just go to the air handler and use the size that fits the air handler, or?
So here's what you could do. You can get a cut to fit adapter plate, and I have a video on how to build adapter plates. So a 14 by 25 is one that you want. These things aren't hard to cut or put the trim kit on. I mean, it'll take you 5 minutes. So I actually made a video, and what I used was a pair of straight tin snips for like the whole build. Like that's how I built the adapter plate. You could take a cut to fit, cut it down to a 14 by 25 because it'll make that size. And anytime I could make one like that, I would do it if I'm going to see it very commonly. Other things to consider, I've had some really radical questions about this. Have you guys ever worked on, I've done these a bunch in my life, like the water source units that just mount to the ceiling with all thread going through them, and they had the filter built into the swinging door. I can't think of the name or brand, but anyway, it's a really funky air filter install. It sits under like 2 springs or whatever, and a guy called me. He's like, man, how the hell am I going to use that for this? So I advised him to take a cardboard box, and he had a cut to fit adapter plate. I said, cut a hole in the cardboard box, tape your cut to fit adapter plate to it, and just make a flow hood. I was like, it'll work just fine. And so that's actually in our manual for this tool that you can do that. So that's what he did on that weird, odd situation. So something else we're kind of thinking about too.
Yeah, I could definitely see some flow hood potential.
Yeah.
With this kind of technology.
But nobody at TC likes me to call it a flow hood. Because we don't want to give it the name flow hood, even though I feel like that's kind of what we'd be doing with it. You know what I'm saying? But there's real flow hoods. Ours would always need a correction factor when being used, so it can cancel itself out, which is kind of what you want to have happen.
Yeah, gotcha. Awesome.
Anybody else got any other questions?
Well, we just have a few concluding slides here. I'm going to share my screen again. Thank you, Chris, and feel free to stick around. And Chris and
I got ice cream left, man.
yeah, that's right. All right, let's see here. Sharing my screen again. Talked about the True Flow Grid. So best practices summary, sort of where the rubber meets the road. Here's what maybe the checklist, or not checklist, but the list of goals that we want to have as contractors and technicians. On new installs, let's go through the ACA design process. Perform manual J, S, T if we can, and D. All right. So we go out to sell a new system, start at the J, take the time to do it, figure out a way where you make money doing it, where you're not doing it for free, where you're not doing it, giving them all this information just so they can hand that information over to your competitor to cut your throat. Figure out a way to do this and make money on it. And what you're going to find is probably the people that'll let you do it are the customers that you want anyway. Measure total external static pressure. Make it a goal to measure that on every job. And then make it a goal when you can to be able to measure total flow, supply and return flow. So these are some things you want to have the option as you start diagnosing comfort problems. Have the tools to measure this stuff. But static pressure, it's a manometer. It's low-hanging fruit. So we see this is sort of like, this is where we want to get to as contractors. You saw the pricing there. It's probably not money you got in your pocket today, but it might be money you could set aside very quickly. It's the end of the year if you're a business owner. It may be a good capital investment or tool investment. Bump it up on that wish list. Compare the readings. So after you design a system using manual J, S, T, and D, you came up with your manual D. You came up with your target static pressure, your target CFMs. Compare your design readings with what actually took place, and you're going to need this to do that. So you can figure out whether you're designing systems correctly. There's no point in designing a system if you're not going to verify that design with commissioning. There's no point. So if you're going to design, be able to verify the design, make that part of your startup and commissioning process. On existing systems, measure total external static pressure on every job. So on new installs, the goal is to get here, and we quantify that flow. We use things like MeasureQuick. We want to verify that flow and do a commissioning process. On existing systems, Measure total external static pressure on every job, maybe even pressure map, because you're going to find things like dirty case coils. You're going to find stuff that you never found before. You're going to find dirty heat exchangers that you would never be able to visually inspect unless you ripped out the unit. Give attention to fittings that are close to the air handler. So think about those supply plenums, the janky flex connections that come off of them. That's low-hanging fruit. Those are things you can sell that are ethical, that will have a quantifiable performance bump. And make it a goal to measure the total flow in every startup. Okay, so every start, this is our goal here, is we want to be able to quantify our airflow. That way, when we walk away, we documented the system's performing the way we want it to. So these are sort of our goals. This is how we make better. All of y'all are here because you want to be better. And I'm teaching this class because I want to be better. Me teaching this class sharpens my skills because I still have a contracting license. I still go out and put in systems. It's not what I do every day anymore, but I want to be better. And so these goals, I've got these goals too, but this is how we get better, y'all. And include duct improvements and duct replacements on more proposals. So when you start measuring total external static pressure, when you break this thing out on your service calls where people say, you know, it's just in July, my house isn't getting comfortable, it can't reach set point. Instead of reaching for your manifold gauges and checking superheat and subcoolant first, maybe pull this thing out of the truck first. And make it a goal to improve your ductwork. Ductwork replacement is not fun. They're in crawl spaces, they're in attics. I get it. I shied away from it for a long time because I was afraid that if I sold more duct jobs, my guys would quit. That's a challenge. Figure out ways around that. And I did also, but figure out a way to sell more duct improvements, because I guarantee you this is the low-hanging fruit that people don't want to or are afraid to or don't have the tools to be able to diagnose. This is our last slide. When you have a high-efficiency system on a bad duct system, this is what you got. You think this Prius is getting 60 miles a gallon on these monster truck tires? No, they're not. Duct system improves these 4 things. This is the 4 tenets of the National Comfort Institute: safety, health, comfort, and efficiency. I've got that all over my marketing stuff as well because I love it. We want to attack and practice HVAC in this order: safety first, health of the occupant, comfort after that, and only then a nice byproduct is efficiency. When you flip efficiency up to the top, it throws everything out of whack. So I want to get input from y'all. I want to get at least one answer per line item here. How does a good duct system improve safety? Chris's hand's going up. We'll see if someone else is brave enough first.
Okay.
Cody?
In the South, humidity plays a big part, and so focusing on airflow to ensure that you're controlling not just temperature but humidity as well makes a big difference. Chemicals and building materials, and I mean just degradation of building materials as well. So
Yep.
I feel like being able to verify your results makes the project safer at the end.
Yeah, absolutely. When we think about safety, anybody else before I weigh in?
I got one for you, Tim.
Okay.
Eliminating zonal pressure issues, which would prevent backdrafting of appliances.
Stole mine, man. Yeah, let's say you got a water heater in a mechanical closet, and in that mechanical closet, you also have a furnace, and you got a bunch of duct leaks in the return. That furnace could be, or that air handler could be pulling backdrafting the water heater. Even if the air handler is not located in the same mechanical room, it could be in the attic. But if you've got a bunch of supply leaks and not as many return leaks, your house is going to go negative. Your natural draft water heater is also going to go negative. That's when I think about safety, the first thing that comes to mind is carbon monoxide, because health is, we think about indoor air quality. That's more of a health thing, but it can be a safety thing also. Anybody else?
Yeah, I was just going to say,
Yeah, go ahead.
Tim, whenever you're talking about duct systems, anytime your duct system is under higher pressure, every duct leak is going to leak more CFM under the higher pressure. So think about all your duct work, your equipment, anything that's outside the envelope, like the thermal envelope, anything that's exposed to let air leak outside. I always say like 1 CFM out equals 1 CFM in, but under a higher pressure, that's going to get worse. So, duct systems may choke out the blower, but what they're also going to do is they're going to drive infiltration if there's duct leakage attached to it.
Yeah, exactly. Anybody else before we move on to health? And the health is kind of tied with that also. We've got some comments there, but any other comments when it comes to health? I like the pulling VOCs from places, pulling attic air, pulling in particulate matter when your ducts leak. But also going back to safety, there was a comment in the chat also. You got a restrictive duct system, your furnace is going to run hotter. It's going to maybe even trip on high limit. How many times is it going to trip on high limit before it doesn't? That's a safety problem. Comfort. That's a pretty easy one, right? But let's talk about it. How does a good duct system improve comfort?
You don't notice it.
Right. You don't notice the duct system even there. We had a comment about humidity. Humidity is comfort. Yeah, we're going to deliver the air where we want it so people stay comfortable. And finally, efficiency. How does a duct system improve efficiency?
Lower amperage on the blower.
There you go. Think about that ECM motor. The PSC motor, when it sees a bad duct system, it says, all right, well, whatever. I'm still going to pull 1,100 RPMs, whether there's air in the duct or not. But the ECM, speeds up. It's going to try it or die trying. And so, yeah, efficiency. And really, when we're reducing how much airflow we're moving through the house, let's say we got a PSC motor and it's not moving the airflow that it should, even though it's pulling lower amps, our unit's also taking longer to cool the house, so the energy bill is going to go up. Compressor is going to have more run hours in the summer than it would be if we actually move the air where it's supposed to. So don't ignore the ductwork. Look for ductwork, because I guarantee you the company that serviced that customer before you didn't. And so there's probably low-hanging fruit. They probably sold them on a media filter. They could have put the little magic blue light in there. But I can't tell you how many times I've seen the magic blue light in ductwork, and there's gaps in the ductwork 6 inches away. You can stick 2 fingers in. I mean, it happens all the time. So that's how we set ourselves apart. That's how we become high-performance contractors. That's how we get out of the trenches. And we stop fighting for the same old customers that don't care about craftsmanship. We step ourselves up to the next level for the discerning customer, the one that does his research, the one that is just looking for a contractor that speaks the language they speak, that they can trust to be competent. We become that contractor in the market, and we're cut above the rest. So thank you for, I believe that's it. That's our class. Above the rest. So thank you for, I believe that's it. That's our class. Thank you for everything. If there's any other questions, we can go over them. We can go back and look at another slide.
Yeah,
Yeah.
I got a question that Chris and I spoke about a while back. Why does load calculation JS&D software calculate variable friction rates?
I know Rooftop does. There's a box you can check to do a variable friction rate. And I can't speak for it. I don't know if Russ King.
Russ is here.
Yeah, Russ is here. I don't know if he's active on the. There you go, Russ.
Why would it not be beneficial if you're doing it longhand to do a variable friction rate? Simply because it takes too much time?
I'm going to let some of these guys that are a little smarter than I am answer that.
I think
Mistakes, maybe?
Oh, go ahead.
I think doing it a variable friction rate by hand may be super cumbersome. That's a hell of a math equation. I think you have to have software to do that, in my opinion. What do you say, Russ?
I think the old worst case comes from back before we had software. Now that we have software, it's super easy to let the software calculate a friction rate for each individual run.
Yeah.
And if you look at, say, Tim, you look at your layout and you look at the shortest run and you look at the longest run, and imagine those two runs needed the same CFM. What you're saying is they need the same size duct. And that's probably not the case. I mean, it does take a lot of equivalent lengths to change a duct size, but there are times where you have a really short run that needs 100 CFM, and that needs one size duct, and a really, really long run that needs 100 CFM, that's going to need a different size duct. And the only way to account for that is a variable friction rate. And it's super easy to do with the software. So that's what I always have done. So
Now, from a manual D standpoint, because we were doing this, on the speed sheet, and that's why I didn't cover it. I always check the box and like right solve, but is there a way to do it longhand with manual D? Is that even possible? Or because I've never seen a variable friction rate in the manual D process.
Yeah.
In the book.
Maybe in there, but
you'd have to look at each register and take it all the way from the register all the way back to the return grill and calculate the equivalent
Right.
lengths for
you're
every
pretty
single
much
of those
doing
things.
that whole process that we did for TEL for times 20 if you have 20 supplies. Yeah.
Right. But the software does it pretty much
Right.
instantly.
Because it's true. Like in my living room, I've got two 8-inch that dump air into my living room, and I've got them specifically sized to go up the peak of the cathedral ceiling where my ceiling fan catches it. My ceiling fan always just kind of rotates. So all I'm trying to do, not trying to throw air to the other side of the room, just trying to throw it to the peak. But when I installed everything, it was with all my dampers wide open. And I had an imbalance. In fact, my static pressure was like less than 0.2 inches total static pressure, like less than 0.1 inch. But I was really cold in the living room. The air wasn't getting anywhere else. So once I throttled them back, static pressure came up a little bit. And so I probably could have gotten away with a 6-inch, but the software told me 8-inch, and who was I to argue with it? So, but yeah, you're absolutely right. There are a lot of cases, and that's why we put dampers in systems, because it's really easy to add friction. It's really hard to take friction away after it's been installed. Is that accurate, Russ, Chris?
Very much. Yeah, absolutely.
Okay. Yeah. Yeah. Great question. I'm going to go grab a beer. You guys are welcome to grab a beer and come back and pop a top, and we can tell some more war stories and ask some questions. But give me just a second. It's been a long day for me.
Same here, dude. I'm still working.
We're way ahead of y'all.
Oh yeah.
I was talking to Alex Meany about because on RightSoft, there's like a magic button you have to hit to be able to access a variable friction rate. It doesn't just show up, I think. There's like a control sign, I don't remember what it is. But his explanation to me was that it keeps people from making mistakes before they understand what they're actually doing. Because a lot of times if you have a friction rate and you check that box, you may be at a 0.06, and then you check that box and then you're back to a 0.1. So it's what they put in the software to keep people from making mistakes. Or at least that's how he explained it to me.
Hey there. I'm surprised I haven't heard anything about a hot wire anemometer. Is that what it is? A hot wire thing?
Yeah, I probably should have put that in there. I was kind of putting in slides at the very end. I wasn't going to get this much into diagnostics, but I ended up doing it. But yeah, you're right. That's a good suggestion. I should put that in there. A hot wire anemometer is, I guess you can use it on trunk also. There's traversing of the duct that would probably need to happen, right? And then you get your regular pinwheel anemometer that you would use for supplies. But there's some room for error for those, right? I mean, I used to air balance with a pinwheel anemometer, and it was really hard for me to get consistent results that I could actually trust.
Right. I figured that there's probably better stuff now than a hot wire, and also I've got one of those CPS pinwheel things that Bluetooth in it, and it's depending on where you hold it, you'll get different results. But I use it to get an average or an idea.
Yeah, I mean, like you got a 90 boot that's under a floor, and you can hold that little anemometer in one place, and it's spinning like a top because that's where all the air is coming out of it. And then when you hold it closer to the inner part of the 90, the inner throat, it might even spin backwards. And it's like, what do you do with that information when the thing, if you wanted higher airflow, you kind of hover over the part of the boot that it's spinning faster with. I mean, there's so much room for error there. I don't know.
Right.
Anemometers are great when you have an answer that you want to get.
Yeah.
Yeah. When I was with the HERS Raider, a lot of times, it'd be like, uh-oh, I need a little more air out of this boot. Let me hover around the better part of the boot a little bit more. No, yeah.
I would say I would add this piece of info that I've learned since I've been at TEC. So just full frontal, like I've been in trade my whole life. And then the last 2 years I've worked for TEC, strictly working underneath engineers. And here's what I've learned. You really got to read the specs of tools. Like you got to get in and read the super nitty gritty details. And once you start reading into the details, it's amazing how many products are on the market that appear that they can take all these measurements until you read the fine print, right? Just because it pops up a number doesn't necessarily mean the number doesn't have some good literature that says, oh, it's accurate at full scale or accurate at partial scale. And it's like, what the hell does that even mean? Right? I've had to go to my bosses and be like, what does that even mean? Like partial scale, full scale, like what are they getting at? Until like Steve broke it down for me, I'm like, well, shit, that means this measurement doesn't even really matter. And he's like, yeah, exactly. He's like, but it wouldn't sell tools if that's what it said,
Yeah.
It's pretty wild that's the world we live in, you know?
Now, I
Marketing
remember
out
years ago, I bought a manometer because it had more numbers behind the decimal point than the other one on the shelf. Doesn't mean those numbers were accurate. We talked about that. It was a random number generator. It was just a better random number. It just generated more numbers randomly. But yeah, you're absolutely right. And that's why it's like having a community like we have here where we know that anything that comes out of TEC is going to be high quality. We know it's going to be, we just know to trust certain tools because they're not going to sell us crap. Whereas if we don't have a community where we know the people that are developing this, you just don't know. You'd have to read the nitty gritty specs, and who are going to do that? It's the Wild West out there. So
I have been using the field piece manometer, and it's been fairly good to me, and it has helped me to diagnose and fix some airflow issues in the past.
absolutely, I used one for years. It was that one that I bought. But when I compared it against a micromanometer, I realized when you're reading things like pascals, mine was not accurate in the Pascal range. It was great for reading static pressure on units. It was great for reading certainly manifold pressure on furnaces. But there's limitations. That thing's also going to bounce around in the tool bag a lot better than some of the micromanometers out there that may get out of calibration when, your tool bag gets air melted off a roof accidentally because your helper did tie a good enough knot when he's lowering your tool bag off the roof. There's certain tools that are going to stand up to that a little bit better. So there's a trade-off.
There's a need for both, to be honest with you. There's just a need for both. There's a time to dig out your micromanometer, and there's a time to dig out your $100 basic manometer. There's a time for both of them.
Mhm.
If you're going to check backdrafting, or if you're going to go do dominant duct leakage testing, which is kind of another level we don't have to get into in this, but there's like, man, 14 tests to a house I could think of that you could do to test a house with a micromanometer that you can't do with a basic manometer. But at the same time, there might be something I wouldn't want you doing with a micromanometer. You know what I mean?
Yeah.
And we have a range. Like I'll tell you, I've checked into our sensor technology that we use for our micromanometer because I really wanted to say you could use it to measure like propane, but I think our sensor stops at like 10 inches of water column, I believe. And I think propane, you got to be between like 13, 15. So you can't use it on that. So that's the one use case I get, I kick myself in the butt and be like, man, I wish we could get a sensor range that'd be a little higher than I could say it's all purpose, but it's just
Yeah.
not. It's just not. You can't get that caliber of sensor to meet that full scale.
Yeah, the DG8 is just it's so compact too. It's like, because the other micromanometers are a lot larger.
Oh yeah, we sell one, man.
Yeah.
It's like 3 times the cost of the DG8.
Right. But I just like the small size of it also. So,
Yeah.
Yeah. So it's one of those things where you may not be able to buy all these tools tomorrow, but like any other tool list, it just needs to be on your wish list. And maybe it needs to get bumped up the list a little bit, hopefully after this class, especially with that coupon code.
And I'll
There's
just
a long wish list in this trade.
Yeah.
Spend all my money on tools.
Yeah.
Yeah.
And I just want to reiterate what you were saying, Tim. Like, look, I'm not going to be the first one to bash to say, like, look, here's the thing. If what you have is a manometer, you got to start somewhere. And that's the place to start. If that's what you got in the tool bag, use that bad boy and start taking pressure measurements, go into the blower charts and start there. Like, that's a great place to start. You know?
Yeah. I mean,
A few questions.
yep.
Yeah, static pressures. Yeah, those have become important to me. Measuring, because I have found that static pressure is sky high on some units, and I absolutely do believe it was the reason why the compressor went out. I mean, it's safe to say that poor airflow or restricted or supply vents being closed everywhere except for one because they want to push all the air to one room, that can contribute to killing a compressor. Is that right?
Well, the compressor doesn't really care about all the airflow going to one room, but the total airflow across the evaporator coil is probably the unintended consequence that the
Right.
compressor is seeing because it's flooding out.
The return air is messing with the compressor.
Yeah, it's just not getting air across the evaporator coil, so the evaporator is not getting the heat it should need, and so your refrigerant isn't boiling off. So you're sending liquid refrigerant to the compressor.
Right. Another thing, let's see. I hate it when I find this. The return air duct is just the gas furnace has just got a hole cut into the furnace itself.
Yep.
And right above, and the return air duct is installed right above the blower.
Yeah.
I mean, that can't be good for airflow.
Right. No, it really isn't. Really anything above 3 ton, you need to either be pulling from both sides of the furnace or the side and the bottom. If you got a side return on a 3.5 ton unit or a furnace is moving 1400-ish CFMs, that's not enough of an opening to a furnace. You've got to pull from both. But definitely the 14-inch hole that's cut inside the furnace, yeah, that's bad news.
Yeah, or on top, it just looks bad, and you destroyed. I'd like to see a return plenum installed,
Right.
but my gripe is that I point all these things out to owners, and I give them a quote, and they're like, I can't do that.
Yeah. And,
but you documented it, which is saving you from
Right.
Documentation's key, man. Like my time in the trade, every time I could write something down and then go back to it when that customer would have a complaint, and I could say, hey, look, I quoted you on this. It's not my fault.
Absolutely.
I did my service. I gave you the option to do more. You
Yep.
chose not to. This is on you. I hate to be the person. I'm not that guy to say like I won't warranty my work, But at the same time,
Right.
if there's negligence and you can prove it, then yeah, then you're not warranting work.
Yep.
No, I've absolutely become very anal about writing all that down. Definitely.
Yep.
Quick question. I mean, I'm in the Houston area. We don't use our heaters much. And this is my last one. Combustion analyzer versus just running the heat for about 15 minutes and using a field piece CO detector and just, putting it against the supply vents, and just testing to see if I can't detect any CO that way versus what I've seen before, combustion analyzers, where I guess there are more up north where people depend on heat to live, where it might need more thorough testing where you're punching a hole through the flue. I mean, am I okay to a degree with just simply running a CO field piece detector and running the heat for 15 minutes, and if I don't get any blips, I'm good?
Well,
Yeah, babe, would ya?
Go ahead,
I love
Chris.
you. Oh, I do love you so much.
Are you asking? There's two questions kind of embedded into one here. Are you saying you're trying to protect them from CO poisoning, or are you trying to commission the furnace to make sure it's working right?
Well, during a heat inspection, I'll run around with the CO detector, and while it's heating,
Mm-hmm.
and just to make sure that it's not emitting any CO
Yeah.
while the heater's running.
This is my just feedback, and I'll be the first one to tell you combustion is not my strong suit, but I've learned a lot sitting in the NCI class. Luckily, and I've only lucked out from this. I've gotten to sit in that class a few times through to the relationships we have with NCI. So David's always like, "Hey, you want to sit in?" I'm like, "Yeah." So I soak like a sponge when I go sit in that class. And it's amazing how much thought goes into a combustion analyzation test with that tool and what you can pay attention to and what you can find out with like a solid, 20 minutes of the combustion analyzer running it. And I know that sounds like a lot of time on a job, 20 minutes of looking at combustion, but their research on combustion is next level and amazing. And there's situations where a furnace runs, and then after so many minutes of runtime, the numbers will then begin to change, and that's when problems show up. And you can pick that apart in their combustion class. Like if you ever sit through NCI's combustion class, they will walk you through how watching they have tables on all this and exercises in their booklet, and it says, furnace ran for 15 minutes. These are the numbers. The next 10 minutes, the numbers went to this. What happened? And they walk you through that problem. And I was like, whoa, because I had never done that in my life. Like I'm learning something new when I sit in that class. I'm like, whoa, like that's next level stuff. That's how much they know about combustion. Like in my mind, they're the all-stars of the combustion game.
Yeah.
Is combustion analysis a requirement for commissioning by the manufacturer?
Oh, good question.
According to ACCA, it's considered a standard of care.
Yeah, I don't think it's. I don't know. I'd be lying if I told you I knew the answer.
Yeah, I don't know the answer off the top of my head. I will say that you're doing half of the test. So you're doing better than someone that's doing none of the test. You're at least trying to protect the customers from CO that day when you're there. The combustion analysis also tells you how much CO is in the flue pipe. And that CO can tell you whether you've got a bad, or the oxygen. If you got too much oxygen in the flue pipe, it can tell you that you've got a ruptured heat exchanger. It was something that you may not even see visually. And you may not even see it with with testing for CO in the supply duct. Because think about it, where is a heat exchanger on a typical furnace? It's on the return intake. So if you get a hole in your heat exchanger of anything, you're actually going to be sucking oxygen into the heat exchanger, not spewing CO out. Doesn't mean that CO is not going to get back into the house, but there is a lot more reasons for checking combustion analysis other than just occupant safety. If your system is blowing out a bunch of CO out of the flue pipe, that CO can make its way back into the house through openings in the house. You don't want a lot of CO in your flue pipe. It means it's not burning clean. It's reducing the life of the furnace. So there's a lot of things there that you're leaving on the table. With that said, when we used to, like in Greensboro, we were 50% gas, 50% heat pumps. Once we set up and commissioned the furnace, we didn't go back and do a carbon monoxide or a combustion analysis every year until the unit got to about 5 years old. It was just not something that we did, but definitely on older equipment, that was something that we did every time, because it would, I mean, you would find heat exchangers, you'd find all kinds of problems, overfired furnaces. We found a lot of overfired furnaces.
What do you do with that?
Well, it depends on what you find. So if you find an overfired furnace, the first thing you're going to do is check manifold pressure.
Let's say manifold pressure's on.
Change nozzles. It changed nozzles because it could have come with the wrong nozzle. They could have done a propane conversion kit but not put in the nozzles. They could have, I mean, there's a lot of things that can happen with that. So again, it's not only occupant safety, but it's also equipment. You know, you're trying to protect the equipment. So I would say that it is important. It's something we started doing. We were probably the only company in Greensboro doing combustion analysis on PMs, residential. It's just something that we did in commercial industrial, and I just carried it over when I started my business in residential. But I get it. A 2-year-old furnace, probably, you're not going to find a lot of problems in a 2-year-old furnace.
I've simply never done it before, because I was always of the mentality, why would I want to know all this data when I only have gas pressure to mess with? And the manual says I set gas pressure to X. I set it to X. I have nothing else. I can't do anything else with it.
Right. Yeah, that's the thing about a furnace. You can only adjust gas pressure and airflow.
Yeah.
You know, older furnaces, you could adjust the little primary air and secondary air shutters, and you could really fine tune that thing like a big boiler. But they took all that away from us. But I could tell you how many 20-year-old, 15-year-old furnaces that I found with a cracked heat exchanger, and the only way that my technician found it was some really funky readings on the combustion analysis. And then when we finally pulled the furnace, we looked inside, and sure enough, and it is a condensing furnace where you can't even see the primary heat exchanger on a condensing furnace. You can't see past the secondary.
Are you going to see other symptoms of a cracked heat exchanger before let's say you don't do a combustion analysis? You're going to get rollout or something visual is going to happen that you're going to pick up on that without doing the combustion analysis.
The colors of the flames, maybe.
Maybe not. It's
I
the
can touch
combustion
on this a little bit.
Yeah, it's you may or you may not. I mean, like I said, we found furnaces with bad heat exchangers that the only way that we found it was because we did the combustion analysis. None of the other items, the flame color, the checking the flame color when the blower turns off, you know, that's sort of looking for that little flicker. Nothing else happened. It was because it was running 1,000 parts per million CO in the flue, and the technician even backed it down to 2 inches of water column, and it did not make a difference. The other thing that it's going to find, and you may find this with flame color, it'll catch flame impingement against the heat exchanger, because you're going to run a high CO because the flame is hitting the side of the heat exchanger, and you see some orange tips in a flame. Is it normal? Is it not? Some technicians are just going to walk away from that, but that carbon monoxide test in the flue is going to pick it up.
One thing that I was pushing towards the end of my full-blown AC career, which was over some time back, any furnace I sold, I included a low-level defender.
Oh yeah, that should be standard operating procedure, but unfortunately it's not. So good for you, man.
Also, how the hell did we get on combustion? This is supposed to be a manual detail.
Yeah.
Yeah, I've had these questions for a long time, and I was
That's all right.
an opportunity.
That's all right.
That's what you do during Beer 30.
Hey,
Right.
Tim, are you just gonna email us the the stuff?
Yeah, so it'll we're still recording right now because some of these questions are really good. So this will be in the recording, and then it'll get emailed tomorrow. It takes hours to process this video for some reason. So what you'll get is an email with a link to YouTube, but it is a private link to YouTube. It's not something someone else can pick up. But I've got to edit out the top secret stuff that Chris presented first. So that'll happen tomorrow.
All right, cool. Appreciate it.
Did you guys see the, go ahead, I didn't mean to cut you off.
No, well, the last thing I just want to say before people start signing off, and I just want to make sure I catch it in the recording, please go on Google. I'll try to send you a link also. Leave my company a review about the training portion of it. This is how I earn a living. So the company is Comfort Science Solutions. I'll make sure I include a link in the email. Please just give me a 5-star because I'm also trying to market to local HVAC companies here. And this helps me, this helps my company. It helps me gain company rankings when somebody needs a service call and that sort of thing too. So just please leave me a review. But I'll leave you a link in the email also. Just please take a moment and do that.
I need to correct my statement because I don't want to make Alex Mini look bad. It's not the variable friction rate, it's the velocity adjustment for the equivalent length that is the magic button in there. So
Alex Mina will kick your ass next time he sees you.
yeah, I said, well,
I don't think I
if
caught
Alex
it.
ever sees this, I don't want to say, man, I didn't tell that dude that.
Yeah.
I want to say the variable friction rate is probably, Russ could maybe speak on this, but that's probably a standard option. I would imagine.
I think it is.
Yeah,
It is.
but the velocity showing, are you saying like a secret toggle button to show the velocities?
Yeah.
Like it will show you the velocities per duct, so you can then manually change them.
It doesn't manually change. You'd have to ask Alex exactly how. 'Cause he told me there's like a control 0 or something that you hit, and it gives you this option. But it doesn't come standard. You have to actually. So I put it on when he gave it to me, and so now there's a checkbox there for this that you can check. So if you're worried about your friction rate, you can. It takes like I'm assuming every fitting and your total equivalent length for every run, and breaks it down. And so a lot of times it's giving you, I guess maybe I don't understand it that well, but I'm assuming maybe worst case scenario, but then it tells you what, with the big picture, what you might actually be at. So the way he explained it to me was, if your friction rate is a little bit worrisome, you can use this toggle button to see what it might actually be in the field, and that gives you a little bit more comfort in the design. He said, but don't leave it on because that will lead you to some poor duct design if you're not paying attention, or somebody doesn't know what they're doing. But it's not the variable friction rate, it's the total equivalent length. It's actually velocity adjustment of fitting equivalent length. And it's in your duct preferences. And it has to be activated. It doesn't come standard. You have to hit control something and then it pops up.
Because I know in RightSoft there is a box that you can check for, and mine's always checked for use adjustable friction rate.
It is.
About
Yeah, it's
something.
always checked. Yeah, I popped it up right after I said that. I was like, is that what that was? And I popped it open. I was like, shit, that's not even what.
And also the thing to remember is that manual D, those like the total equivalent length or total effective length, I always forget which when you use the word equivalent, when you use effective when I'm talking about these. But it is based on 900 feet per minute through a fitting. So,
Right. Well, that's what he said. That was. I'm glad you said that because that was his words. Was that it's
Yeah.
based? Everything is based on 900.
right.
Which
That's
is not
manual D. That's not
entirely
RightSoft. That's manual D.
Right. And it's not entirely accurate. So by clicking
Right.
this box, it then takes your actual duct design and figures it out. And a lot of times it puts your friction rate in a more ideal spot. He said, but don't design it with this selection on. Design it like normal, and then if you're a little worried about it, you can click the box, see what your actual fittings produce, and then you can say you can either thumbs up or thumbs down and redesign it if you need to.
Sounds like they built in an equation to reduce or put in the appropriate equivalent length for fittings and things based on the velocity. They obviously have like a
Right.
velocity correction factor going on. And
If I
know
if I knew how to
velocity-
share my screen, I'd show it to you.
But
But I don't know.
here's my thing with that. Bigger duct's never a bad thing. And you're not going to get crazy amounts of heat gain from having one duct. What that's going to do is maybe adjust some ducts by one size, basically. Okay, so if you're dealing with, let's say you got 10 runs on a system and you've got 5 ducts that could be reduced from a 7 to a 6. In the whole scheme of things, who cares, right? Like, why do you want to make that slight change? The price is almost irrelevant, and you're going to have a better chance of not having a failure on your hands by running the bigger duct, and you could balance it to perfection. You're not going to get the heat gain on surface area of the duct doesn't even come into play when you're talking about 6s to 7s with 5 runs out of the total install. It's just a mute point. So like I get that feature's there, but that's like really getting into the weeds.
Yeah, which is I think why they hide it. You have to activate it because of exactly what you just said.
Yeah. I mean, personally, I mean, it's fun that it's there, but like, I would never use it. I just wouldn't. I just couldn't see the benefit.
Right.
Talking about heat gain of ductwork, is that a standard calculation, like a round ballpark, or is that actually calculated per run, so forth and so on?
That's probably a Russ question. I will tell you, I've done a case study on that this past summer. On my dad has a house behind his house, and I did a full-fledged case study on a AHRI certified system that we installed. Duct leakage was like 20 CFM. I put field piece probes in the attic, and I data logged the attic temperatures, the outdoor temperatures, the indoor temperatures, and the longest run, the shortest run, the medium-sized run, to see what impact attic heat would have on ductwork. And the furthest temperature difference I could get, if I remember right, was either somewhere between 3 to 5 degrees. I don't remember, but it's noticeable in my opinion. 3 to 5 degrees is something noticeable.
Yeah.
From the plenum to the first drop, which was 5 feet, there was literally no temperature drop. To the middle drop, it was like 1 to 2. So in my opinion, when you have and this is like at 130, 135 degree attic when this was going on, the first 10 to 15 feet, you may or may not gain 1.5 degrees. That run that's about 20, 25 feet, that's when you start to see 3 to 5 degrees. And I don't know if that's because the last 10, 15 feet make that much difference, but that's what I noticed during that case study. I still have all that documentation, but it's buried away somewhere and I had to go dig it up.
I've noticed it too. I've gotten myself in situations where I've had to, like Tim said, get rid of some fittings to try, because one, more importantly, I think they were just long runs where we were losing probably 5 degrees in the end. And so we've had to make some adjustments on that, but where our delta was the same, we had a 18 degree delta close to the unit, and then we were losing 5 degrees at the furthest run. So I know it is something that we deal with. But
Man, I ain't heard no war stories yet, but I'll tell you a fun thing my dad used to tell me. My dad used to say, if we ran ductwork and air moved really slow through the system, his belief system was lazy air makes ductwork sweat. How many of y'all have heard that? That was my dad's mentality. Lazy air makes ductwork sweat. Air moves slow. And then I had an engineer later on in my life correct me. And he goes, Chris, he's like, if ductwork sweats because air's not moving, fast through the ductwork, he goes, why doesn't a cooler or a freezer sweat? That air just stays in the box. And I was sitting there thinking, I was like, damn, you make a good point. He's like, because man, velocity, he's like, he goes, it's all about the thermal barrier, right? He goes, that's what you got to wrap your head around. It's all about the thickness of R value and the air tightness. The movement of the air is kind of irrelevant. that was a hard lesson learned. Yeah.
Russ, going back to duct tape in an attic, what kind of math is involved in there? Because I know what Manual J is kind of evolved over the last few. What do you have to say about that?
Yeah, read section 23 of Manual J, and what you'll find is that it's really, really complicated, but they also take some really, really big assumptions.
Yeah. One of the biggest assumptions in Manual J, I think.
Yeah, it really is. I mean, if you wanted to really nail it down, you would need to know what percent of your leakage is on the return side and what percent is on the supply side. Nobody knows that. I mean, you could guess based on the length of duct, but nobody knows that. And that has a big impact on it. That affects whether you're pressurizing or depressurizing the house. And nobody knows. So that's a huge assumption. And then, where the leaks are and all this other stuff. So it's a really complicated thing. And my philosophy is just do the best you can, do a good design, do a conscientious design, and all those things kind of get hidden away in the
Russ, what section did you say?
23, section 23.
23.
Yep.
I did an
A couple
experiment.
questions.
Go ahead.
I was just basically I was a service tech for like 8 years, and then I started my own business for the last 2 years. So what I did when I was still a service tech, I took ACCA's design class, went through the whole Manual D, Manual J thing. The thing I kind of found hard transitioning into that, like doing Manual J, is trying to size things right. Like, am I wasting my time doing like a Manual J if I'm not getting a true infiltration and duct loss test? Like,
You're not
that's the
wasting
thing.
your
Like, I was,
time. No,
I was,
think there are some purists that look. The more information you can gather and the less assumptions you can make, the more accurate you're going to be.
yeah,
At the end of the day, you're taking, what WAG stands for. It's a wild.
Oh,
Yeah,
that's yes.
you're turning a WAG into a swag by doing it.
yeah.
You're putting a little more science into it. You're taking a little less assumption, but heck, man, I mean, we can get into the minutia of Manual J's. How do you know behind that wall that that's actually R13 and that the installers didn't compress the R value?
Yeah, that's the other thing. Like,
Filled with
you don't know if those are true R values. Like, it's just a little overwhelming sometimes. And like all the houses in my area, like I live in Pennsylvania, and like there's so much different construction around here. It's crazy. Like every house is so different.
Just do the best you can. I'm going to be holding my Manual J class again, probably another month or two. But anything that a Manual J without infiltration is still better than 2 ton, 3 ton, 4 ton.
Yeah.
I mean,
I get that.
for the streets. So I mean, you're not wasting your time doing it.
If I could do one test on a house, like if you ask me, hey Chris, you got 2 minutes, go into this house. You could do a load. What would you do with that load? What would you do? Like if you only had 2 more minutes to spend in that house, I tell you what I would do. And this is something you might have to go research, but I would do the room pressurization checks with a manometer, a micro manometer, so I could see if I got room pressurization problems. And then I would turn the air conditioner on, shut all the doors, check the main door to outside to see if the house is going negative or super positive, which is going to kind of tell me if I have a dominant duct leakage problem on the return of the supply. It won't tell me if I have balanced leakage, but it could tell me if one's super bad. And that lets me know if Pandora's box needs to be opened. It's not flawless, but for 2 minutes worth of time, it tells me a lot. That's what I'd do if I had 2 minutes on top of a load count. Then like if you need to put the brakes on and do further testing.
And if you had 10, 15 minutes, do a blower door, and that test in the context of a blower door, because you could have a house that doesn't show any dominant duct leakage, but has tons of return or supply duct leakage, but the house is so loose you'll never pick it up with the manometer.
Right.
That's what I was getting ready to say. In reference to with reference to outside, you can have a house that's so damn leaky that you're not going to pick it up because it's making it up so fast.
Yeah.
Right. There's nuances to everything, man.
Oh, yeah.
Every test has a nuance to it.
Yeah. But yeah, I mean, you're right. It'll tell you something. And definitely when you're doing comfort consults, if they're saying, well, this room is always hot, close the door and throw a manometer tube under it. And
That's probably the biggest issue that I see day to day is zonal pressures.
Well, in Louisiana,
We also have like, I'm sorry.
no,
Go
I
ahead.
was just gonna say we live in central main return land, right?
Yeah.
So, and we have the problem with not enough return air paths. So, you got to know your market,
Yeah.
right?
Yeah.
Like if your market is central main returns, then you should know what you want to test going in. You should have this feel for, well, you're going to be the king of jumper ducts, basically. Like, and you're going to know that's your move. If you live in the land of oversized furnaces, then you're the man of manual J's and reducing furnace tonnages.
Well, we just have everything where I'm at. That's the problem. We have some ranchers with attic units. Then we have development houses with systems in the basement. And then we have boilers. And it's like, there's just like a million things you need to know in this area. It can be a little tricky.
Yeah, you guys in the central part or either central East Coast or like Midwest, you guys get it all. You get the harsh
Steam
winters,
boilers
you get
and radiant
hot
heat and
summers, you know what humidity is, you got a little bit of everything.
attic units. Yeah, it's
Yeah.
crazy. But it's just tough.
Yeah. Earl had a question about blower door tests. Do we see a lot of them? Unfortunately, we don't see enough of them. Here in North Carolina, they wanted to put it in the code that just passed, and the Home Builders Association was successful in striking it from the code. So we are still going by either 2009 or 2012 energy code. So, and then there's other states like, I can't remember what southern state, like the deep south, that you were like, okay, yeah, they're not doing blower doors, and it's mandatory. But here in North Carolina, I think it's got a little bit to do with culture, and it's got a lot to do with how strong the lobbyists are. But we don't get enough of it. Russ is from California. They're ahead of everybody on that stuff, but it's regional. That's why Chris says you got to know your region. Yeah. Good question though.
We're seeing a lot more of them recently. We do a lot of production home, track home, and a lot of the stuff that we're talking about, whether it's building performance or whether it's load calculations, that just doesn't get done in that market. But what I've seen is that whenever you are doing the load calculations, blower doors, etc., that gives you a little bit of a grounding to know, like, you're a little bit more confident in the performance of your system. So if you have a calculation and you can test the performance of your system and it meets the calculation, not saying that it may not be a problem with the install or the air conditioner, but that gives you a little bit more confidence to say, like, I don't know if this is necessarily an air conditioning problem. This might be a building problem.
Yep.
Well, then you utilize tools like the blower door, infrared, zonal pressure, things like that. And then you can point out some issues that these builders are experiencing.
Yep.
If they bleed enough and if they have to spend enough money fixing these issues, we've got a fairly large builder here that when we started with them didn't do duct glass, didn't do blower doors, didn't seal elevation changes, didn't do anything. The last 2 years that we've been with them, we pointed out enough issues that we're talking to them in meetings, like even today. They're talking about installing doors, windows, and hanging sheetrock on the ceiling, stopping production, and then running blower doors at this point. So the transformation for some of these contractors is huge, but it never would have happened had there not been somebody that stood up and said, I can't fix this with air conditioning. This is not an air conditioning problem. I've checked the load calculation. I've tested the equipment to make sure that it's doing what it's supposed to. I think we need to start looking elsewhere, and here's what I suggest.
Yep.
A lot of the issues of people not seeing the value in these tests, I feel like, just come from ignorance, just not knowing it. Your ducts are sweating in the attic, that's an AC problem. No, it's a building problem more than likely. It's a ventilation issue.
Yep.
You need a 4 ton in a house that should have 2.5 tons. I don't think it's that the 2.5 ton isn't any good. I think it's that you've got a leaky house and you've got zonal pressure problems and you didn't seal elevation changes and things like that. I think that if you work with them long enough, you start to see that ship start to turn. And so I think, I think that's where you have to start. I know that some of the larger contractors that we work for, they're coming around slowly, albeit, but they are coming around. And every now and then they surprise me after working with them for years. Some of the things that they say, like, hey, we'll hang the sheetrock and run a blower door test halfway through the project. And I'm like, what did you just say? You know, it's the same company that wasn't running blower door tests 2 years ago.
They're not coming around out of the kindness of their heart. They're coming around.
No, they're coming around because they're bleeding money. Yeah.
Because of litigation. And
they're used to being able to throw it on the AC guy, and you know it's the AC guy's fault, and the AC guy is not educated enough to know that this is not really his problem, and so he just can't figure it out.
Oh yeah, and he lets
so
himself
there's
get
this
beat up.
ignorant kind of I don't know and I don't know, and then that creates an argument, and in that argument ends up this AC guy gets fired and this contractor hires somebody else. But the moment that you start solving the problems and you start educating and they see that, well, he said this was the issue, we paid him, right, which is a big part of it. Like, now I'm not warranting this, and I'm not working for free. I'm getting paid to do this. They're now bleeding a little bit of money to fix this issue, and their ears start listening a little bit more, you know. And so we've seen some major changes, especially on blower doors, because of stuff like that. But it always takes somebody I did a lot of work for free to prove some of these things before they started paying me to do it, but it was a necessity. I had to, so that at some point they would say, all right, you know, call them in and let's have them go look and take a shot at it, and you know, and we get paid for that stuff now.
Yeah, there's a lot of people who make a pretty good living doing that. Whenever every HVAC design or installation on new construction, when you're working for a builder, should come with a documentation saying this design is based on the following criteria. Like when I do an HVAC design, I mean that's like 70% of my business now is, I mean, I'm not even the installing contractor. I'm doing designs all over the country. So I had zero control over all this stuff, but I have a design criteria worksheet that I get a signature on. And it spells out everything that's going in the duct into the load calculation, the entire design, including what the target ACH is going to be. And it's like, look, if this design does not work, don't call me until I've got a verified blower door test and a measure quick commissioning. And that's my out. You know, they're not doing measure quick. Like, don't call me, tell me this house is not comfortable until you show me a measure quick commissioning. Because how do I know that you guys didn't even commission it correctly? And now I'm going to pay for a new system or a bigger system and so again, that came from sewage flows downhill and the subcontractor is unfortunately at the bottom of the hill. And so when things don't work, the owner yells at the contractor yells at the sub, and the sub is like, well, I guess I missed my load calculation, or I guess I got to rip that 2-ton out, put a 3-ton in. And he doesn't have any tools to prove that's not his fault. And he doesn't have any documentation just to show that, no, that the house just wasn't built right. And so that's what this education ultimately is, protecting ourselves. But I don't understand the resistance to it.
Yeah. Well, we got there through problems that, hey, your AC is not cooling the house. Yeah. And where that would have, you know, those are opportunities. So as long as you're fairly confident and look, I did a good load calculation. I commissioned the system. I've got a measure quick, and that's our first step. So when we do a load calculation and somebody calls and says, hey, I'm not happy with the performance, the first thing we do is a measure quick. So we go in, we ensure that the system is performing like it's supposed to. If it's not, we make the correction. If it is, we go back to the contractor and say, look, I double checked my load calculation. We verified system performance. At this point, on the top of every load calculation I do, whatever their target blower door is like right under their name and address. It says it is the responsibility of the contractor to ensure that this dwelling meets this ACH.
Yep.
And so that's the next step. So there's a process that we've learned to protect ourselves over the last couple of years that we follow every single time. And typically that opportunity comes from somebody pointing the finger at you saying your AC is not working properly. And then you have to be ready and have that process in place to be able to go in and say, actually, no, it is. It is working correctly. And this is what I think we need to do moving forward.
Yep.
Eventually, the customer screams enough that they'll throw some money for you to go do the testing just to make it look like they're doing something. And then lo and behold, you find, 18-foot foyer is not insulated or, whatever the case may be. You look hard enough, you'll find something,
Yeah.
something's going to pop up out. But
Well, the next thing that's coming is in-home mold tests are going to open up. The lawyers are going to have a field day with that. And again, sewage flows downhill. So who's going
Right.
to get blamed for all the mold problems with these leaky envelopes and all that? So yeah, it's going to be. I had a few problems when I was doing Energy Star work. I didn't do any new construction unless it was Energy Star. And
Right.
even Energy Star lets you dump raw outside air into return plenum. And it was killing us during shoulder, or not even shoulder season. It was killing us on a June morning that was, humid and a bunch of dew on the grass, and we're bringing in outside air, and the AC's not running. So I finally, again, I ran too many service calls trying to solve humidity problems that weren't my fault. And Energy Star was like, look, that's proved. You can dump return air all you want into a return plenum, no dehumidifier needed. I just started. It was an offer to client. It was like, look, I'll do this job, but I want to put in a dehumidifier. It's going to be $4,000 extra. And then they would decline it. And then it came with, okay, don't call me when you need when it's humid in the house. It's like the subcontractor has to protect himself, but the subcontractor is usually the last person who has the resources, the experience to know to do that. I mean, most of these subcontractors are just guys like you and me, or guys just starting out doing new construction. They don't know to have a legal document drafted. They don't have $2,000 to pay a lawyer to draft up a legal document for that. They don't know to do that. And then they end up getting stuck with all this because they have less lawyers on their team than the other guys up the food chain have. And that's
No. Yeah, and with all that you were just saying, we're right in the middle of all that. I mean, that's a normal day to us, I won't go too further into that, but yeah, we're dealing with all that stuff right now. Even with the Energy Star, we do a lot of Energy Star houses.
Go to Cody for all your legal needs.
Yeah.
And like the jobs that I'm designing, I'm designing LEED jobs. Now LEED does require a dehumidifier for every space, so that's a good thing. But a lot of this stuff is just Energy Star, and there's nothing. Energy Star allows you to oversize a unit, a single stage unit by 120%, a two stage unit by 140%, and a variable speed by 160%. I mean, those are tolerances that go way beyond manual S, and Energy Star is like, yeah, we're fine with it. So just because a house is Energy Star doesn't mean it's energy efficient, doesn't mean that it's a high performance house is what I mean. It does not. And everybody is ignoring part load performance.
Yeah.
It's only design temperature like a few hours out of the whole summer, and the rest of the time. Now, I'm not talking about April and October. I'm talking about a June morning where we've got all the latent load, and I swear, like I'm starting on my designs. I look at the design conditions, ASHRAE design conditions, but the very next thing that I look at is the mean coincidental dehumidification. I can't remember what it's the next line down. And I look at that, and that's what I size my dehumidifier for, and that's what I'm looking at. I completely decouple it. I'm like, you know what, air conditioning unit, you don't do latent anymore. If you do it, fine, it's a little bonus. But I'm not expecting you to do a darn thing on latent. I am expecting you to just handle sensible, and I'll get a dehumidifier to handle latent because I can't trust you. I can't trust that a variable speed unit and part load operation is going to have anything less than a 99 sensible heat ratio. It's just
I can work
they don't publish it. They don't publish it either. So how can I trust you?
I can tell you, I mean, I'm not bragging brands, but my Daikin Fit in my house, I've actually measured it with a True Flow at different ranges, and I've watched it maintain the same sensible heat ratio from like a third of capacity all the way to full capacity of like sensible heat ratio, and this was Measure Quick spitting that number out to me, but I want to say it was like 0.65.
That's pretty good.
Well, Nate Adams did the same thing. He did the same thing, and he got the same result. So he had on his podcast, he was talking about the Daikin Fit and said that he was blown away.
Yeah, that thing will suck some moisture out. even at part load. And that's not true across the board, though.
No.
They don't all do that.
Yep.
They'll get a little bit more aggressive on their water removal capacity and low speed. I would say limited experience with Mitsubishi on one of their lines is a little bit. It's crazy because it's not necessarily the brand; it's the unit itself.
Yeah.
Right. There's when you get into the inverters and you start looking at tonnages, one thing you should start paying attention to as you start designing and getting really critical is looking at their submittal sheets. They'll have minimum capacity, right? So like I was designing a job for work we did. It's going to come out. It's going to be a video on it and all that. But anyway, I was trying to decide between a 2-ton and a 2.5 ton. And I want to say the minimum capacity on the 2-ton was going to be maybe like 18,000 BTUs, and then the like 2-ton was going to get down to 13,000 BTUs. Well, that was kind of like a noticeable swing because I was looking at how much runtime would I have in part load condition, and I was looking at my my 1% dew point ranges, which was in this climate was around 70. So I knew I was going to be dealing with moisture, in part load condition. So the decision was it was a decision where I had to say this was the dilemma. If I would have went with the 2.5 ton, it had way more heating capacity. I almost could have had no electric heat needed for this job. That would have been awesome. But I would have gave up my runtime and part load capacity that I needed to get rid of moisture. I wanted to tackle the moisture problem more than the heating problem. So I went with the 2-ton and installed electric heat, and the electric heat is going to stage in when needed. And I had to make that sacrifice because of moisture. And so that
in a
minimum
southern
capacity-
climate,
This was in Virginia.
Virginia. Yeah.
Yeah, and think about northern climates where they have the equivalent of, I don't know, 4 tons of, I know we don't talk about heating in tons, but like you need a 4-ton heat pump to heat your house. Well, you only need a 1.5 ton to cool the house. What do you do? And that's the problem that we're going to run into with all this electrification without proper training, is that they're going to yank out a 2-ton air conditioner and they're going to put in a 4-ton heat pump on a duct system that's not made for a 4-ton heat pump, and on a cooling load that's not made for a 4-ton heat pump. And they're not even going to use a cold weather heat pump, and it's going to be a disaster. Earl had a question. And we can keep talking about this, but I just wanted to share my screen about how ducting a dehumidifier. You can go on any Santa Fe dehumidifier, the Ultra series, in their manual, they'll show you how to duct it. But like when I design a system, this is one of the details that I make out of CAD. And so, and I always use a Haven to control it, but you're bringing in your return duct, step up to a media filter, coarse air handler. Here's your dehumidifier. Your dehumidifier is going to pull a return. Now, preferably it's going to have a dedicated return out here, but practically wise, you can't do that all the time. You're going to pull a return. If you can pull it off at a 45-degree angle, remember we talked about T's versus Y's. You can do that if you can. I always put a little bit of flex duct in there for noise and vibration. Make sure you put a backdraft damper in here, because when this blower's off, you don't want the air handler doing this, turning it into a bypass. And then you dump it back. And actually, this needs to be revised. Santa Fe is suggesting that we dump it into a 45-degree angle. Again, this dehumidifier has to fight this static pressure, has to push against it. And the Santa Fe's have a beefy enough blower they can do it. But I can tell you other brands that don't. And so, and a lot of other brands will have you pull from the return and dump back into the return, because they know good and well their fan can't overcome the static pressure. So as long as you got a decent static pressure, you're not running like a 1/2 inch on the supply side alone. You throw it to a 45-degree angle, it'll mix back in there. But this diagram, Santa Fe gives it, it's got you a diagram on that. Just go by that. And
I've put in a scoop before, right where the supply goes into the supply. I've just mounted like a scoop. That way it's not just deadheading it. It's got almost like a scoop to run out. It's just cheap, efficient way to avoid all that velocity
Do
pressure.
you calculate the pressure loss on that fitting when you do your manual D?
That's exactly right.
Tim,
Yeah,
do you add the CFM from the dehumidifier to your total system? Or do
I
you
haven't.
just dump it?
I
Well-
haven't. There's not a great way for me to model it in RightSoft. Now, maybe somebody else is a better.
Well, let me ask you a question. Why would you add? Are you saying you want to add the load to the DHUM to the total load?
No, I'm talking CFM.
Would it actually add CFMs to it? Because you're running it in parallel. So
Well,
Well, if my dehumidifier is moving 150 CFM, and I dump that 150 CFM onto my plenum, my system's moving 150 more CFM.
yep. Yeah, I can see that. I haven't done CFM. I do look at mixing temperature because and not to that's a good question. I think we should probably
That's a good
do
question.
more of that.
I would ask.
Bypassing the blower.
I would ask a couple questions. Like, when are you going to see that install? Are you saying you're going to see it on single stage, or mostly non-single stage, mostly inverter, right? And the idea behind a DHUM is to not run when the air conditioner is at full
Right.
tilt.
Well,
Right.
the way I install mine, I run the Haven control, and my blower on my DHUM's running 24/7.
Yeah. Yep. That'd be an interesting video to make. How, take a true flow grid, quantify your total airflow, and then unplug your DHU and see if it changes.
Now, let me say this. I did do a job a couple of months back running high static, and I didn't do my due diligence on the front end. And she called me back having issues while I installed my dehumidifier. I did increase some of the size of the ductwork. I changed some of the fittings. I took out some pressure boxes and put Ys. So I made some huge improvements to the duct. I installed my dehumidifier with a 45-degree takeoff backflow on the top of the plenum like I always do. She calls me back about a couple months later saying, hey, something's going on. I went back out and I started checking static pressure. This freaking thing was running 1.1. So I started kind of panicking, and I'm like, well, what the hell's going on? So one of the things I did, I checked my static pressure with my dehumidifier running and off, and it didn't move.
And your DHUM's dedicated air, not pulling from the return air.
Correct. It's a dedicated return. So basically,
What was your supply static running? What was your pressure on your supply static?
let me see. I just freaking had it up.
Could be it wasn't moving enough air because when you're talking about airflow and pressure in a duct, let's just say you're running which doesn't sound like it because you're running 1 inch, but if you're running 0.3, if you add 150 CFMs to that, the ductwork may be so big that 150 CFMs doesn't nudge the pressure.
I didn't check the supply side. I checked between my furnace and my coil, and I was running at 0.6. So right before the coil, which, like you said, I should have checked the supply.
Yeah. The supply is critical because if you're running a really high supply static, your DHUM, it's like hitting a brick wall. And the DHUM is trying to force air, but it can't get it in there. So now the DHUM is, you bought a 70 pint, you're getting 10 out of it or something,
Yeah.
I mean, that's a whole nother, are any of y'all going to the symposium, the HVAC school symposium?
By the time I found the freaking tickets were for sale, it was
Sold
out.
The only way I got in is I'm presenting with Nikki Kruger. Because I got in, I figured, all right, I'll wait 2 months before it, then I'll go. So, but yeah, I'm presenting with her. And that's one thing I'm going to talk about is supply static pressure, but also just the fact that we can't size these things based on their nameplate information. Just like a Carrier 3 ton ain't 3 tons. All right.
Tim, have you ever read the case study done by Andy Ask on DHUMs? If you haven't, I'll send it to you.
I've read a few. I just don't recognize the name.
Yeah, he did a whole. He's the guy who basically said if we would go supply to supply for a dehum, and the literature shows, man, like because your air coming out of your air conditioner when contained in a duct, the humidity is super high, right? Because it's boxed in. And if you send that straight to the dehum can remove moisture like a beast, and then puts air right back in the supply. It may go into defrost more, but it's still way more efficient. The problem is a dehumidifier will probably sweat. So it's got to be in conditioned space to make that happen. But it's like probably the most efficient way to install a dehumidifier. And he wrote a whole case study on that.
I think
Who was
I've
that?
seen who's the guy? Ryan Marks is like an engineer, used to work for Thermistor. He may have referenced that. I think I've seen it, but yeah, send it on. That's interesting that you would. But now wait a minute. Now if you're dumping cold air supply out of your air conditioning supply into a dehum, there's not a lot of humidity left over for the dehum to pull out.
Well, there's it's been a while since I read the article, but there's still moisture in the air. The relative humidity is super
It's
high.
saturated.
90 something. Yeah, you're at like 90 something percent. So
The
that
dew
water
point's super low.
but there's still moisture there, I guess is what I'm saying. So
Yeah.
like you have a better chance of it sticking to the coil, I guess is what he's saying.
Yeah.
The RH
I got
is
it.
super high.
I got a question here related to that.
Mhm.
What is latent heat? Latent heat is energy, right?
Yeah.
Right.
The structure has a certain amount of sensible and latent energy. What's the difference where I pull it? Whether the system, the AC system removes that energy or the dehumidifier removes the energy. The energy's being removed.
Are you asking what's the best way to do it? Because the air
Well-
conditioner is a better dehumidifier than a dehumidifier. It's more efficient. So anytime you can have your air conditioner be your dehumidifier, that's what you want to do.
Unless you got to run strip heat, and it loses all its.
Hey, right. Yeah. Unless you're having to do reheat as an option.
So it's my understanding the latent is representative of the water vapor that it's drawing out of the air. That's the energy conversion there. The latent heat of, I guess this wouldn't be a vaporization, but the opposite.
Right. But if you're pulling from a supply duct, there's not as much food for the big dog to eat.
I hear what you're saying. I'm looking for it now. If I can find it, I'll send it your way.
I thought Santa Fe was recommending that recently, that they had moved where they were wanting it ducted in. See if I can find that.
Supply to supply. That'd be a first.
Yeah.
Because when you look on a psychrometric chart, your dew point is a lot lower. Yes, your RH is high, but your RH is not moisture droplets.
Mhm.
Your dew point,
Right.
the grains. I mean, your dew point grains are the same. They're just opposite sides of the.
I follow.
Chart.
I'm with you. I follow you.
But any temperature, it then drops that air. It's immediately water coming out of it. There's not a sensible load. It's got to get down before it gets to.
Yeah, I do see that. Yeah.
This gets into an area I'm not familiar with, like the actual hardware function. Can it handle that lower temperature? I don't know.
It's going to go
I
to
think
defrost.
This goes way back, but I remember talking to an engineer at Santa Fe quite a long time ago, and he told me that their coils and their fin spacing is different than an air conditioner, and it can handle much colder temperatures before it goes into defrost.
Yeah.
I don't remember the actual numbers, but it can perform better than an air conditioner for longer than an air conditioner.
So here's a question. We all know what happens if we dump a dehu supply into the air handler return. We're dumping hot air on our cooling coil. We kill the capacity of the cooling coil, right? Because coil temperature goes up. We're not doing a lot of work, right? But what if it's a Bosch unit that sees that increased coil temperature and automatically speeds up the compressor? Because that's how it speeds up the compressor, is it's trying to maintain a 40-something degree coil. Would that not? I've got a Bosch unit. I just got done repiping my whole dehumidifier, and then it dawned on me in the middle of the night. I'm like, well, I can't do it now, but I want to see what happens. I mean, yeah, the Bosch unit's going to pull more amps, but again, it's sort of the best dehumidifier in the house. So why wouldn't I do it that way? Now, another inverter unit, any other inverter technology, they speed up the compressor based on deviation from set point or superheat or something like that. But the Bosch is like, got a higher suction pressure, don't care why, I'm speeding up my compressor. And so it would just compensate.
And doesn't the air conditioner dehumidify less though in a low load, because you're actually ramping it up when it should be ramped down. So then it might the AC might dehumidify less. I don't know. I'm just throwing it out there.
It seems more of a sensible load, but I mean, my dehu's running anyway.
Yeah.
We
don't really do much dehumidification up north, so I'm not my strong suit, but I do a lot of Bosch units.
Yeah.
Say that one more time, Tim. You're saying if you do a dehum and pump the supply into the return of the
Yeah. So I turn it into a mixed air temperature, right? I'm dumping in 105 degree air, mixing it with 75 degree air, depending on the ratio. Maybe my entering coil temperature is now 85 degrees, 90 degrees. Well, a typical AC unit is just going to run a higher suction pressure, but my Bosch unit is going to see that higher suction pressure and say, no, you got to bring that back down. And
yeah, but I'm just thinking out loud, that's where my brain's going. If you did that, you'd be displacing some of the recirculated air you could be pulling, because your Bosch unit, let's just say, is only going to move a certain amount of air.
Right.
So if you displace the air you want to pull from your house with hot dehumidified air, then you're attacking sensible load and you're letting go of the moisture you could be pulling from your house from the displaced air that you're bringing in from the dehum.
But my dehum is pulling return also, so wouldn't that cancel it out? And it's dehumidifying it. I mean, that gets into some.
Yeah,
I don't know. It's an interesting thought.
it's an interesting thought.
The Bosch is the only one that reacts like that. Everything else, I get it that it's not going to work. But
Tim, one of the videos or something you posted about reconfiguring your dehumidifier.
Yeah,
You zoned it to where it'll do the attic and the house without communication.
Yeah.
I was wondering, why are you even concerned about the communication between the attic and the house?
Because I'm not convinced that isonine is good for you.
Okay.
And so I'd rather not cut a supply duct in my attic, because then what does that do? Well, it creates a pressure difference. One way or the other, isonine air is getting in my house, whether I suck it through a return or whether I do it through. So I wanted to dehumidify either my house or my attic, but not both.
Like when I do mine, me personally, I don't care. It's going to communicate. I encourage communication. However, I always install a dedicated dehumidifier just for the attic.
Yep. And I'm cheap. So there's that.
Cheap insurance, brother. Buy a freaking $1,500 dehumidifier and throw it in your attic.
Yeah. No, this was more also, this house is my test lab, man. I want to try different ideas that I would not, and I said in the video, I don't recommend doing this as a contractor until.
Well, that's why I wanted to ask, just to clarify, were you actually concerned about it, or was this just an experiment?
Yeah, I was concerned about it because it's me and my wife here, and I don't want us to develop cancer 20 years from now when we figure out, oh yeah, sorry, it's asbestos all over again. So who knows? And I mean, look, I've taken some instrumentation up there, and I don't read any VOCs coming off of. I don't read anything off gas and off of it. But I don't know. I just didn't want to do it, so I just wanted to see whether this was possible and if it would work.
Yeah,
the real test is going to be, and the other reason why is I wanted to be able to show people how humid the ridge of a spray foam attic gets.
Yeah.
And
You
so
have a data logger up there?
well, what it's going to do is I pull when it goes into attic dehumidification mode, I pull a duct from the top of my attic.
Yeah.
So I run it through the Haven. So every day at 2 o'clock or whenever I tell it to switch over, we're going to see a spike in dew point in Haven, and we're going to see how well it brings it back down. And I'll just let Haven do it.
Speaking of Haven, let's go down that rabbit hole with the ventilation control. Haven's only controlling ventilation when the total VOCs get up. We need something to give us constant ventilation, and then you can give us a spike when VOC spikes.
I know. I'm talking to them about it. The other thing that I've noticed here in my house is my VOCs are fine, but my CO2 was through the roof.
My CO2's been freaking sky high in my house.
So
Mine's high too.
yeah,
Are you doing comparisons based on a different meter? Because
well, it doesn't read CO2. I've got an air things on here, and my what I found out about my Ecobee thermostat, it's not a real CO2 sensor. They're actually converting VOCs to CO2. So the air things, see you, Cody. So yeah, I had to get something that actually read CO2, and I also want something that talked to IF to if this then that, because then I can get a little Wi-Fi relay. So I just texted Kevin yesterday. I was like, dude, you need to get the controller on if this then that, because I can hook up my air things and ventilate to that. And he said it's in the plan for 2024, but it's not their first concern. Yep.
Tester or whatever you want to call it. Because I live literally 100 yards from I-12, the busiest freaking interstate in the South. And I was concerned about carbon monoxide.
Yeah.
So I was expecting carbon monoxide to be through the roof, and I don't have any, which was a freaking surprise. However, what hit me like a slap in the face is the carbon dioxide is through the roof.
Yeah. Yeah. Ours is just because my house is really tight. And
Mine isn't. I'm a 7 ACH.
Yeah. Well, speaking of carbon monoxide, this is the first since I started ventilating to get my CO2 down. I posted this on Jennery's Facebook group. Actually, well, yeah, still reading zero. We've been in this house for almost 6 months, and my carbon monoxide personal monitor always reads 3. I take it outside, it goes right back to 0. And I'm like, we're all electric here. For a good while, we weren't even parking in the garage because we were still moving in. All our crap was in the garage. I'm like, where is it coming from? And it wasn't until I started ventilating more to get my CO2 down, and now I'm at 0. So I don't know what the cause of that is. I don't know if there's something that's off-gassing, that's cross-communicating with the sensor, but all I know is since I started ventilating more because of CO2, I probably ventilate 70% of the time now instead of 10%.
So
it's gone.
What is your thoughts on this? S-Ray 62.2 says I need 50 CFM of ventilation for this particular house. I set up my ventilating dehumidifier with the Haven control, and I manually open that damper to move that 50 CFM continuous and just let the Haven fully open it when it needs the boost. Is that a good...
Yeah, and I like that's Joe Stiebrick says that he thinks that ASHRAE 62.2 is a little bit overkill for continuous ventilation, that he suggests maybe continually ventilate half of that, but have the capacity to ventilate up to 3 times of that on demand. And I agree with that. And I've seen that in my own house. Like, I probably should be ventilating a little bit all the time.
Yeah, that's the way I feel about it.
And I'm sorry, it helps pressurize my house. Like, why would I not push moisture and contaminants out of my house doing that? So I would rather, if I had to do it all over again, I would have ran a 10-inch outside air out, and I would have had a 2-position damper, 0, 50, 100, or whatever, like what you're saying. And the Haven would go between 50 and 100, and then it would operate between 0 and 50 anytime pretty much all the time.
I mean, now that I've seen my personal house, the carbon dioxide levels the way they are, like I want this freaking thing ventilating 24/7, damn near as much as possible.
Yeah.
And we all know the indoor air quality is freaking crap in our houses, so why would we not want to ventilate it as much as possible?
Yeah, I tell you, I've gone full circle on this because when I was experiencing all those Energy Star House humidity problems, I was like, there's no reason we should be pulling in this much fresh air to a house where, it's like, okay, fine, we're diluting VOCs, but we're creating mold. Well, the answer is we needed more part load dehumidification capability.
Yeah.
And actually, we do need ventilation in
But
houses.
are you allowed to do that in an Energy Star house?
No.
Right. You
Haven is not Energy Star approved. They want you to be they do not approve ventilation on demand. It either needs to be continuous or it needs to be intermittent, but intermittent like on a timer, not on demand.
Well, if you do an Energy Star house and you go throw a 98H in it, you take a penalty for that, right?
I think so, which is stupid.
Right. It's asinine.
Yeah. Yeah. That's why I don't. This is what happens when you put energy in front of safety, health, and comfort. This is exactly what happens. It's a war on sensible heat, and you end up making stupid decisions like that. You penalize somebody for moisture control.
My huge argument to all this is controlling moisture. I take controlling moisture of utmost importance over anything else. If you can gain and can control the moisture of the house, you're building a sustainable house there. You're building a house that's healthy for people. It's not going to kill the people in it. You know what I mean?
And you do that by tightening the house and controlling ventilation.
So you'll get the byproduct of that is going to be an energy efficient house.
Yep. But,
you can't have the reverse though.
Right. It doesn't work in reverse.
Right.
You can't put energy in front and expect to get comfort and health and all that stuff. Yeah, they'll penalize you. And that's my whole problem with it. And then when you work in, like, part of what my business does is I review designs for Energy Star and lead jobs, like in the Cincinnati market. And so I look at other guys' Wrightsoft deliverables and make sure they're compliant with ACA 310 or Energy Star or LEED, and you're looking for things that they missed. You're looking for, they oversized the unit and that sort of thing. And you see that really the mentality in that whole world is, look, you're going to get your Energy Star certification. We'll fudge the numbers if we have to, but you're going to get it. And it just defeats the whole purpose of having it. So you turn it into a certification mill instead of doing what's supposed to do, which is deliver a better home.
Yeah.
And it's unfortunate, but
that's one thing, Tim. You touched on this earlier in the presentation, but I'm 30 years old and I tried Wrightsoft and it just seemed so outdated to me, and like it was just a pain to use. I'm serious.
Try Elite, bro.
Yeah, at least
it better.
Yeah, I get it. That's why Russ King, he just jumped off of here. He's the founder of QuickModel, or it's QuickModel, right?
Yeah, that's what I need to try because.
Yeah, and
I paid all this money for Wrightsoft, and dude, it gave me so many headaches. I'm like, I can't even use this. Like, I'd rather do it manually than use that. But I do my load calcs differently. I actually use CoolCalc, which I do a lot of block loads and retrofits. Like, I don't do a lot of new construction, so I found that's a little easier.
Yep.
Also, Carmel Soft for my iPad is pretty decent.
Yep.
But like, I just feel like HVAC is so behind in technology with all like the apps and our phones and everything. It's just like there's so many great things out there, but I feel like HVAC is just so far behind. Like
on every level, not just load calculations, on every single freaking level.
Everything, yeah. I mean, it's just like our technology, like all like these Wi-Fi thermostats and like Honeywell stuff. Like some of it's just so far behind like other home automation systems, and it's like. I don't know why. It's just, I guess it's such a niche. Like not enough people even do it for them to invest all this money in it. But I don't know.
I think that's got a lot to do with it. I think it's, forever this industry wasn't exactly the super money making industry, and now it's starting to get that way. And I think I've heard that like there, maybe in the United States, there's somewhere around 700,000 technicians,
It's not enough of a market.
Yeah, that market's not really huge, to be honest.
So we're stuck with this.
Not that bad.
Stuck with this 90s technology that's just like takes forever. I mean, and then I even got like their Right J Mobile, but like I didn't like that at all. I thought it was like super cheesy. It was hard to like.
Yeah, I tried.
It's because like
It was.
when like I do a lot of swap outs, so like you can't spend forever like kind of doing a block load, you know. So I was trying to make it so I can do a legitimate, but that's like I said, I'm not doing duct leakage. I'm not doing so like I didn't know if I'm just doing a disservice by even doing it.
No, you're not
but,
doing
like,
a
I don't know.
service. Not at all. I mean,
Thing is too, the more you do it, the more you learn.
No, I got a lot better. I've been doing it for like 2 years now, and from the beginning to now, I can do it a lot more effectively. But it's
Yeah.
just I like to do things right, and up like where I live, nobody really. There's not many companies are doing blower door tests and duct leakage. I don't know why, but it's just I feel like in the South, like all these trainings and that symposium, like I feel like you guys, I don't know, just with humidity, I guess, and all the attic duct work, like it feels like you guys are pushing things way more than up here. Like there's nothing up here. It's kind of like a free for all, you know.
It's the same
I
thing
think-
down here, bro.
I think, yeah, it's the same thing down here, but I think what's going on is I've watched like who I've met in this role, and I just watch them, man. I look at John Simmelhack and Neil Comparetto, and I'm just like blown away. Like those guys can probably name their price, right? And they you know, when they walk on the job, like that homeowner just knows. I just hired the ultimate best mechanics I'm gonna get, and I'm gonna get one hell of a job. And I mean, I'm sure it took years for them to get their reputation up there, but if you take that path, man, it's got to be a hell of a good feeling to be those guys right now, you know, to just know like you're the person in the market, people call, you know, when you get the call, what you're walking into, a homeowner who's prepared to pay because you've made that reputation that you are the guy who does things all the way.
Yep. And I say this to a lot of people, I probably should say it more publicly. But I tell people, let Walmart customers have Walmart companies. There's a reason why Walmart is so big because there's a lot of people that's what they want. But when I buy a pair of dress shoes, I go to a men's clothing store a lot. And when I buy a suit, I'd rather go to a boutique shop because I don't want to buy a suit from a big box store. I'm a discerning customer when I buy a suit. And there are people out there that are discerning customers that want there is a Neil Comparetto customer base in every market. You just got to be the Neil Comparetto. And
Yeah. And
you're not going to grow like the biggest shop in town, and you need to be okay with that. You're going to a lot of people say you're way too expensive, you're out of your mind. You need to be okay with that, but you'll find the people.
There's so many cheap customers, you know, they're looking for
They're
the
everywhere.
lowest price. You don't want that customer. And then if it doesn't work right, you're going to be there a million times,
Right.
you know.
I can't even speak their language. I mean, people that are okay when their sole decision is, well, how much is my monthly payment going to be? That's where their decision is. I can't even talk to them. Like we're not even on the same plane. Like I don't
Can you
know how to
itemize
talk to
that
the
for me?
financially illiterate. I don't know what they want. I'm not like them. So I don't sell to them. Yeah. Yeah. Good stuff.
there's a lot of people out there who want the quality install, but they have to understand why they want it. And if you hone in the skill set of, and I'm not gonna say I was no Neil Comparetto when I was in the trade, but like my last probably 5 years in the trade, I did a pretty good job of making my name in my market. You know, I wasn't Neil Comparetto, but I had a good name and I could charge a super premium for doing my installs. But they knew when I came in, it was load calculation, blower door, duct leakage test, install, commissioning on the way out. That's what you got. Like that was my turnkey, super whammy bammy thing. And if you didn't want to do it, then sorry.
Yeah.
I don't
What's
care.
like the best path to get into blower door testing and, you know, like BPI certification? Like if I wanted to start pursuing that, like what's the starting point, you know? Because I mean,
I think
I saw the BPI class, yeah,
BPI is probably, I mean,
is in the area.
yeah, I think BPI would be a good place to start. Get the blower door basics down. Get the total duct leakage testing down. You know, and those two right there, hell of a place to start. Right, once you know those two, that's big. Then you know there's some, and if you want a precursor to that before you go into that, like here's what I'll tell you. Do you have to go get BPI certified? No. Would it probably help your case selling to the homeowners? Absolutely. If you want something to taste it before you get into that class, like TEC has all of those trainings of the, like, it will be tool specific, right? It will be our gear, but those, the testing, how the test should be done. We have those videos all on the website. There's a whole
Yeah,
training module you can watch on our website.
you can learn how to do it without going to BPI.
I guess that's what I'm saying. I don't want to shed, like, I don't want to say BPI is not important. Like, you're not going to go to our website and probably learn combustion safety. Like, we're not going to teach that on our website, right? That's not exactly what we're known for. But if you want to know how to run that blower door, like, we have videos for that.
Let me say,
It's like,
Way more comprehensive.
let me say this as far as testing, and I know y'all probably going to call me down on this. I'm all for testing. I believe in test in, test out, testing for compliance and whatnot. However, I don't need to do a test and collect a bunch of data for somebody to tell me the sky's blue outside. If you walk up to a duct system that nothing's sealed, you got ducts falling apart, like, I'm not going to charge the homeowner $400 to hook a duct tester to this thing to show them your duct's leaking.
Yep.
yeah.
Same thing with a house. I go into a house and I got top plates cracked open, knee walls. You know what I mean? I'm not going to sell a blower door test on that.
Yeah.
Right.
If it's an ACH 50 of 11, there's no need to go and, like, you should have a
Right.
conversation before you do it.
It's just like I have no experience on where these houses really land. Like I took the trainings for ACCA and all that, and they say, just you can tell if a house is leaky or not. You know what I mean? It's just common sense, but it's like how leaky, I don't really know, So it's just getting that baseline. I mean, just
I
kind
don't
of
think
err
you
on the
can
side of
tell.
caution.
You can't tell that a house is tight without a blower door test. You can know. You walk into a 1879 farmhouse, it's
Yeah,
going to be leaky. You walk
Exactly.
into something, you kind of know by the era that the house is built, and that it hasn't been weatherized. You don't see any spray foam anywhere to be seen. It's going to be leaky. So yeah, you're absolutely right. You don't need a blower door to tell them that. But when you do a load calculation, what number do you put?
Yeah.
Yeah, exactly.
Yeah.
So I
I mean, I would always.
same thing with
I would
ducts.
mess around with it sometimes. I would do semi-loose, then loose, and kind of see what my differences are and kind of make some decisions that way. But
Yeah, loose is higher than 11. Semi-loose is like 7 to 11 or something.
I'll tell you what Alex Meany says to that, because we've kind of had a little chat about that. And he's like, if I don't have the luxury of maybe getting money for my blower door to do my load calc, I'm always going to select average.
Average, right?
Because it puts you right in the middle.
That's right.
Well,
And that way, if you're one-sided, you're only halfway off. Right?
Like,
So
I don't know what
that's-
construction's like in your area, but like let's just say like your standard like development house built in like the 2000s, let's say R19 walls, 2x6 framing. Like, what would you expect to like no spray foam, just like your normal R30 attic? Like, what would you expect that to be?
5 to 7.
Like,
Keep in mind, insulation is not an air barrier, so you
Right.
can have R30.
The insulation is completely irrelevant in that conversation.
Yeah, it's basically just not sealed, like no spray foam, no, sealing
but
normally around the windows. You know what I mean? Just like a standard house,
From my experience with it, I would say the house you just described to me is probably a 5 to 7 ACH 50 house.
Yeah, I'd say 7.
Yeah. And then, when you're into a spray foamed house, it really can get radical, but typically I'm seeing 2 to 4.
That's going to depend on who shot the foam.
That's well, right. I mean, all of this is just general talk, but
Craftsmanship related. Yeah.
foamed houses that are nice, 2 to 4. Traditional build houses that with some attention to care, maybe a 4, but probably not. Mostly a 5 to 7. And then houses that didn't get neither, those are wild cards. They could be anywhere from 7 to 13. That's typically what I've seen.
Yeah, I've had a new construction house in Baton Rouge that I tested was like 12 something.
Yeah. What
This was a
surprised me,
custom home builder.
I mean, I went back behind our framers and I was spray foaming and I mean, I had to get on them about rolling zip tape on there, zip system tape. The typical house, love to blower door test my next door neighbor. Their house went up at the same time ours, same builder, just a whole lot different approach to the envelope.
Yeah.
And just see, but yeah, I would say 5 to 7 on a new house built to code right now.
I don't understand these builders.
Huh?
I don't understand these builders. They buy the zip, they pay the extra money for it, and they install it just like regular OSB.
Yep.
I'm like, you just negated everything. You just,
Yep.
you know what I mean? They have no clue. They like it. It's the green thing to do, and they think they're making a huge difference. They're saving the polar bears, but they piss them in the wind, brother.
My framers framed my front porch overhang with zip, but then they ran out of zips and they used regular OSB for the actual envelope barrier that goes in my attic. And I was like, they were just doing it for looks. It just looks good. It looks green from the street. I mean, they just don't know, you know. That's like one of the lessons that I learned is telling the wife. It's like if I had to tell someone else how to do this, is you've got to get a builder that he is a high performance builder. Like he's a stakeholder in this, you know. And if you don't, then you got to be prepared to go
build
above and beyond what you normally do as an owner to make sure you have an airtight house. And my builder was cool. He was not against it at all. He was just like, look, we build the way we build, but if you want to come in after hours and spray foam all you want, have at it. And he let me do it. And you know, I love the result of the house. I just have a hard time getting rid of all the CO2 I'm breathing out. But
I have my general contractor's license now, and I'm waiting for Chris to cut me a big check so I can build his house. That'll be my first high performance house.
I hear you.
One day, man. One day. I told him if I ever build a house over here, I'd let him build it and we'll tag team it together.
That's really cool. It was really fun to put into practice some things that I had just freshly learned. I mean, A House Has to Breathe that just came out. You know, I was looking at a lot of Matt Reisinger stuff, trying to sort through what was actually doable on a budget and what wasn't. And in the end, like the biggest bang for the buck I got was zip system and spray foam in the roof deck. Like those are the two things I have.
You didn't buy a Zender?
Do what?
You didn't get you a Zender?
Ventilating dehumidifier, man.
I think I priced a Zender a while back for one of my spec houses that I was planning to build.
Yep.
Like $12,000.
Yeah, oh yeah. No, I was designing a house in Texas, and same thing. They were eating up Matt's content, and he was like, "I want a Zender." I'm like, "All right, well, Zender does like their own design, like."
Right.
And I saw the bill, and he sent me an email about a week later. He's like, "Hey, you think you could what's the change order to replace that Zender with a Brone?"
You know, they like the Zender has their own piping.
Yeah.
It's like foam core, styrofoam, glue it together. It's wild, man.
Oh yeah.
I don't know much about it, but
Zender designs them. I think your local AC guy or whoever you can get to install it, and then Zender comes out and commissions it.
Oh,
yeah.
really?
That's what. Yeah, I'm pretty sure the commissioning's like figured in the price tag. I think.
Yeah. That's
Like, what's your guys' opinion on spray foaming? Like, let's just say 60s, 70s, 80s construction, like spray foaming the roof deck there. Is that like a bad idea? I mean, I know they say like it can deteriorate shingles and stuff like that faster.
I don't know. I personally, anytime from what I know, okay, about like air pressure, natural movement of airflow in a house, anytime you can put a lid on something, do it, because then you stop stack effect flows.
Is stack effect such an issue where he's at in Pennsylvania?
Oh, if it's cold,
cold winters. Heck yeah.
Oh, that's probably the worst.
Wouldn't it be reversed?
Stack effect in the wintertime, stack effect is up. In the summertime, it's down.
So, I mean, so if you could put a lid on, so this gets really nerdy, but there's such a thing called the neutral pressure plane, right? Which can, like, as it moves up or down, kind of affects the amount of flow you have from stack effect. But the minute you cap the floor or cap the roof, you drive the neutral pressure plane in the opposite direction and you stop the flow, which stops the infiltration. So if I could spray foam the attic and put a lid on the house, that will drastically kill the stack effect flow, which kills a lot of the infiltration. So I would, any chance I could, foam out roof, I would, or seal it. It doesn't have to be foam, but I get that foam's kind of the easiest traditional method to do it right now.
Yeah,
Like,
the
that's-
only caution that I would say, and I don't know how cold it gets there in Pennsylvania, but with cold climate,
About 10 degrees. 10
yeah,
degrees.
see, if you're getting sustained
design.
cold climates, you could have a cold roof deck, and you could have moisture that develops between the roof deck and the spray foam. So I think
Heard
a lot of
that.
cold climates, they'll put a continuous layer of insulation on the roof, on the outside of the roof deck, so you kind of sandwich it a little bit, and then that has air sealing capabilities also. So I would almost consider, in lieu of spray foam, and maybe rip the shingles off if it's around time to put shingles on, and maybe doing something like a continuous. I mean, I
Look
don't
up Building Science Corp. Joe Stebrick's got a lot of articles on that.
Yeah,
So I was about to say
he's in
same.
Boston, so he
Oh.
would know.
Yeah,
But
he's the super knowledgeable person on that topic for sure.
but
Just
either
with,
way,
like the electrification, it's like if I'm going to improve, or if I'm going to put heat pumps in these houses, like you got to improve the envelope, or it's a waste of time.
yeah.
I mean,
Yeah, absolutely.
I do mostly dual fuel because you kind of get the best of both worlds. For at least if they don't want to improve their envelope, I do a lot of Bosch dual fuels, which that was the other thing I wanted to touch on. I don't know, like if you guys looked into their coils at all, but Bosch's coil, if you look at their chart, it's actually pretty crazy. So their 4860 coil, which is supposed to be 4 or 5 ton, the C and D cabinet at 1695 CFM, the D cabinet has a 0.4 static pressure drop. It's 4, yeah. And then the C cabinet 4860 at 1589 CFM has a 0.4 static drop. So that coil is 4 passes deep, instead of 2 or 3, it's 4 rows deep. So I couldn't believe the static, the pressure drop on that.
That was a question that I was going to bring up earlier. When you're looking at a fan table and it gives you everything from a 0.1 to a 0.9, are you allowed to design anywheres within that parameter? If you need to hit that 0.9 because I got a coil that's taking up 0.4.
that's where we
It's
get
okay,
into.
but
It's
probably not ideal.
It's not ideal, but I mean, sometimes you're stuck doing it. I mean, for years I heard people saying if you're designing or if your static pressure is over 0.5, you're a hack, and you start adding up coils and media filters.
0.4 coil.
Like I can't do it. I get it, man. I mean, I've seen people that have designed 4 inch of static in these houses in Cincinnati. When I first looked at it, I'm like, ain't no way. And I start looking into it. I'm like, no, they don't have a choice. This unit's in the basement, and it's a skinny little 4-story house, and all the ducts are like shoehorned in between the floors and going up a chase and then shooting across. And you got 370 feet of total effective length. And they didn't
That's
have
how it
a
is
choice.
here.
Yeah, and so it's, man. I don't know what you do there.
I remember
Every
Aka
replacement-
Ed had made a video talking about just that. Like he said, if the table goes up to a 0.9, you're allowed to design up to a 0.9.
Yep. Just know that your ECM is probably not going to last very long, and you better put a really deep trap on that coil because it's probably going to blow through it.
To speak on that, because I've had this conversation a couple times for sure, is you got to watch the tags. And I've talked to a couple manufacturers about this, and I pray that this comes out and it happens and it takes storm. But like the maximum allowable TESP should be on the tag. And what we're seeing on tags is like rated. Well, rated's not the same thing as maximum allowable TESP. Rated is what it's rated. Like, how did it get rated? It got rated at 0.5. That means AHRI conditions was tested at that. That's what's on the tag. And it's this mentality that means that's the maximum you can run it at, and that's not true. Sometimes the tags might say maximum allowable static is, like 0.5, and that is the case, but sometimes it's not. So you got to watch the literature on the tag. It's not always it's one of the others.
And I would agree with something that like Allison Bales said is anytime you're putting a 5-ton unit in something, it's probably a bad idea.
Yeah.
Unfortunately, they don't design 5-ton units very well. What are the units that always have to have that plate that you got to screw on so you don't blow water off the coil? It's the 5-ton air handlers. You can't build a big enough 5-ton air handler to correct those problems. It won't fit in an attic. It won't fit, through a door. And so I would say is maybe to the point of if you got 3 tons of coolant load, put a 3-ton system in there and let that dual fuel handle the rest. Maybe your balance point's a little higher. But man, I try to steer away from putting in 5-ton units if I can.
Yeah, like really in our area, like they used to, a lot of these multi-story big houses, they used to just put one system in the basement and it was just bad. Ductwork was bad. Everything was done by rule of thumb. They weren't doing friction rates. They would just do 0.1, whatever, high static pressure. So they did kind of get smart and the builders figured out, all right, we'll put 2 systems in the basement, one for the second floor, one for the first floor. So it's gotten better, but you're still dealing with those houses where they finish the basement. You can't access the ductwork. They have a 5-ton. They don't want to spend the money to put in another system. So I'll try to if they put new windows in or updated insulation, that's why manual J is so important because then you can, you could downsize them like an AC size or a furnace size and lower your static substantially, oversize your filter, return air base, I try to make all those improvements, turning vanes in my return boots, open the supply up. I mean, that's what I try to do, but that's what I'm saying. If I'm not really blower door testing the house, it's hard to trust that. Can I trust that manual J to drop them down a ton in cooling if they put low E windows in from original construction? You know what I mean? It's that's kind of my challenge at this point, but it's
I would
worked for
trust
me.
manual J. And the other thing you can do, and we've had a few posts about this recently. I think it was actually John Similak. If you put in an Ecobee thermostat, you can start tracking runtime. And if the unit hasn't died yet, you can maybe that last summer that it's going to be in service, put an Ecobee in there, and it'll tell you what the runtime is on a design day. And you can tell whether that 5-ton unit's oversized or whether, this is bstat.io. It's an open source website. You can connect your Ecobee to it, and it gives you so many more insights.
What is it?
bstat.io. I can share my screen real quick and I'll show you mine on it.
So speaking of design temperatures, design days, we've had, Chris, what was it? 100 days?
More than normal.
Well over 100. Where our design conditions 93 degrees.
Yeah.
Yep, I hear that, but here's my argument to that. We can't say days. We have to say hours when we talk about that because it's not days, it's hours. We see that and we only see it for a moment of time. And as we get in tighter, the construction quality should be better. And when it is, and houses are tighter, once you build up that thermal mass of cooling, when you go into that span of, I've exceeded peak load, it shouldn't even matter. You know what I'm saying? Because the thermal mass is built up and the dwell time is going to last long enough to get you through that peak that it shouldn't have an effect. For example, think about all the houses you've done that are foamed. Think about all the houses you've done that are not foamed. Do your foam houses call you because they don't keep up? I don't have that problem. But you know what I'm saying? But why? Because the house is tight, the thermal mass is in check. They're not leaking air out during peak load and having to replenish it quickly. It's hanging, which means the house stays comfortable. So it's this all goes back to build tight, keep tight ductwork, and you don't even have to give 2 craps about we exceeded peak load 100 days by 2 more degrees than normal. None of that will even matter.
Yeah, I'm not changing my design temperatures.
Yeah.
I'm just curious, is ACCA gonna adjust their 10-year?
ASHRAE does.
They'll have to. Doesn't that? I believe that's ASHRAE data that they go off of every so many years.
ASHRAE does.
ASHRAE's recording all the data, and then after so many years, they basically look at it, and then ACCA probably makes a decision based on the ASHRAE literature of recording.
I mean, the thing is, like you said, let's say they do go up a degree,
It won't matter, dude.
right, that's not making a difference.
Wonder, have you ever gotten a load and changed it?
Yeah, it's nothing.
Well, I'm about to actually. I'll just going to do it just for the benefit.
It's nothing at all.
I bet you won't see any tonnage equipment changes. I've done this.
Oh.
I've went and changed temperatures and played around with it, and I got no equipment changes on it.
Yeah, I'll share my screen. I got my house pulled up right now.
That question I asked earlier about the duct surface area.
What is that old technology there on the screen?
I know it's like 1988 called. They want their technology back. All right, so wait a minute. Let's first go to the. All right, so here's my load exactly how everything sort of stands. I'm at 1.7 tons. By the way, they normally put a 3.5 ton unit in this house, just so you know. Like if the builder's guide put it in there.
Hold on. Speaking of that, did you show this to the builder?
Yeah, I did.
What do you say?
Sit the builder down and explain all this to him, because he's the one that's that makes the changes.
I know. You know a wall when you see one.
But AJ, you know what you're not thinking is, man, for somebody to hear this for the first time who's not even in this trade, it will be so much to absorb. He'll never pick it up that way.
Right.
But dude, look, just that in itself, like you're putting 3.5 tons in your houses when all it needs is 2.
Yep. Let's see. I know it's in here. Oh, here we go. All right. So here's my design temperature. You saw we have 1.7 tons. Let's turn the design temperature to, I don't know, 99. How about that? And my wet bulb to, I don't know, 78. Let's just
say 79.
79, sure. Okay. All right. Now let's go back over here. 1.7 to 2 ton.
Yeah,
that's extreme, dude. That's
go back to that, and that was a pretty high jump on Sensible. Nobody's going to make that jump that fast. Let's take it to where are we at? 91.
Yeah.
Let's just go to 94. I could never see it going.
No, I was being extreme just to kind of.
Yeah. I'm just
dude, after working with
a tenth of a ton.
That speed at which you're changing this and getting data back is freaking like mind-boggling.
Now look, a tenth of a ton for 3 more degrees, and there's no way you'll make a different equipment selection based on that.
Right. Now, I do want to show you guys something that really does drive the needle. Let me put this back. That is, what if we were to say, I want, instead of running at 75 degree, let's make it 72 degrees.
Oh, indoor temp?
Yeah. Or actually, let's make it a lot. I don't know if here we go. Let's make it 70 degrees. I mean, I had just as much of a jump there. I went from 1.7 to 1.9 trying to cool the house.
Yeah.
I mean, indoor temperature matters more. You look at and where it really matters is the extended performance data of the unit, because if the difference between that unit cooling a house to 75 and it having the amount of BTUs and work it takes to pull it down to 72 is huge. I'd rather see a higher outdoor temperature than a higher indoor temperature when it comes to selecting units. But
half-my customers,
I really wish
68.
I really wish Connor and Russ would have partnered with RightSoft or Elite.
They wouldn't have had them. I'll tell you, I think the person still here, we were talking about doing load calcs for replacements. Look into Conduit Tech, because they are a up-and-coming software company. You use an iPad or an iPhone Pro, you use their app, you scan the house, you enter in some information, it does a load calc for you. They're in beta right now.
What's it called?
Conduit Tech. Conduit, like electrical conduit tech. They're in beta right now, but they're working on getting their manual J certification, but that's not easy to do. Like, you got to get all your math worked out. And that's a game changer. So
yeah, I saw your post on that, and that looked pretty cool, because some of them, like even CarmelSoft, is kind of time consuming, because you got to I don't know, it just takes time. Like Cool Calc's a little faster, but it's also a little more inaccurate because you could like map trace the house, but like it doesn't always work that great, to be honest with you.
So-
Like,
I'll tell you a cool feature that I hope to see come full circle with Quick Model is when they take like Cubicasa and you scan the house like with like a company kind of like Polycam.
Yeah.
You go around the house, you scan it, and then you
Yeah.
upload it. And from what I understand, Russ is going to take that and develop a 3D model off of it, so you won't have to
that'd be
draw.
awesome.
Yeah, that would be
Yeah.
very.
Like, I have a laser measurer and there's an app so you can go around and you can hit that and it's supposed to draw out like a architect, like a plan for you, but
Yeah.
it's so glitchy and it doesn't work that well that I just kind of abandon it. But like that kind of concept to me would be the best. You could just go around, beep, 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 beep. It'll have a
Dude.
whole layout of the house.
Cubicasa.
If you haven't tried, I haven't tried Cubicasa, but I've tried Polycam, and it's pretty cool. Like it's-
Cubicasa is freaking awesome. Cubicasa is awesome. I've gotten to where pretty much every call I go on. Now I'm not doing service work, so I'm not running 10 calls a day. But every like performance call I'll go on, I'll scan the freaking house real quick while I'm there, just for the hell of it.
Yeah, I mean,
On your
that's
phone.
what I do with Conduit Tech. I send them the data, and I'll do it spits out the load. Then I crank out a load on RightSoft, and I send them both. That way, they can kind of tweak things. They can see where the differences are. But yeah, like on my comfort consults, and I'd be interested to see what y'all's approach are. My comfort consults include a load calculation, the blower door test, and a measure quick. Like I'm gonna do the load calc on the house. I'm gonna see what the unit's actually doing, and I'm gonna quantify
You
infiltration.
do this on your first visit.
Well, I sell it. It's a service where I make enough money where it's worth it to me. I'm not giving it away.
My first visit, I'll go in. I charge $350. I'll go in, go over the house visually. I'll do some zonal pressure tests, and whatever I see that I need to dig into a little bit more. If it's the AC, I'll dig into it. Walls,
Yeah.
whatever. I'm dealing with microbial growth, so I'm doing a zonal thermal scan. I'm trying to figure out what's going on with the house, and
Yeah.
then from that $350 visit, I'll build a scope of work or more testing if we need to do that.
Yeah, because you'll never sell your first job if the first conversation they have with you, you're telling them $1,500.
Right.
So you sort of have to start small somewhere around there, and you know where it's heading. Like if I walk into a house and I pop my head in the attic and I see exposed, where I see top plates haven't been spray foamed, and I look at my AC boot and I see it hasn't been sealed, and I look at one plumbing penetration, I see that hasn't been sealed. Sorry, we need to test your envelope. Like and so you're not selling work that doesn't need to be done, but you're also screening them really quick and saying, this is what this costs.
Yeah.
You know, 'cause I am a firm believer that loss leaders are, when you go into a job losing money on it, hoping to sell work. I mean, that's how these companies that tell people they need new equipment and sell the $8.99 service call. I mean, that's their mentality, and I think it's really dangerous for us to get into that. And it's fine.
Even if I get a call, just hey, come give me a quote on my AC system, $350.
Yep.
I'm not coming to give a free estimate.
Put skin in the game.
Right. If you can't pay me my $350 for me to come spend 2 or 3, 4 hours with you in your house, then you're definitely not going to pay me my $25,000, $30,000 to do the system.
Right. Yeah, and I mean, it will pigeonhole you. You'll never grow like the biggest shop in the world or in the country doing it, but you'll get the customers that actually are serious about it. And so I think that's where people like us that are wanting to do better work, we have to realize that like the masses aren't ready for this level of intellect yet. The masses are still shopping at Walmart, but we're looking for the.
Yeah. Also, I think you got to decide what kind of business do you want.
Right.
Are you building a legacy business where you want it to be that level of, ethical, or are you building a business to sell? Because I mean, let's just be honest, man. It's like, no offense to which way anybody wants to go, but a lot of those decisions get made based on what you want out of life.
Yeah.
I've talked. I don't know Brian Orwell, but I've talked to him briefly, and I know like Brian has the mentality of I want to build a legacy company. He's gotten bigger. He's one of the few that I've seen get big and try to keep his code of ethics up.
Yep.
While he's doing
It's hard to do.
It's hard to do.
It
but he's
takes a
doing it.
unicorn owner to be able
Yeah.
to do that. But Brian's also not doing a lot of home performance stuff. I mean, he's a demand business. He's a service call business and a breakdown business, and they do a good job at that, and they got a good reputation. But yeah, I mean, the only way you build the biggest shop in town is you have to sell a lot of units, which means you got to pressure your people to sell a bunch of units, which means you're probably selling units that don't need to be sold.
100%. Yeah.
I mean,
We have so many
that's
companies.
the slippery
on my
slope
way.
that you're on.
They go in there with mirrors. They pull the limit out and they try to find a microscopic crack in a negative pressure heat exchanger. And like, dude, the amount of high sales companies we have up here is just insane. They're just trying to push new units, and they don't do
Same here.
any. They don't do any manual J's, and they just swap apples for like 20 grand.
Yeah. I don't have a problem if you want to go and give someone options for a new unit because the unit's over 10 years old. Sure, fine. Include it in one of your options, but don't lie to them. And if you're going to charge $30,000 for a change out, make it worth it. I mean, change the disconnect out. Pull a decent back, do a decent commissioning, do a blower door and a load calc. Don't go in there and like slice into the plenum and bend it so that it fits the new unit for $30,000 and then claim you're the best company in the area.
Yeah, and no manual J, none of that either.
Right, none of that. I mean, I don't charge Rolls Royce prices, but do Rolls Royce work. Don't just say you do.
Yeah.
Yeah.
Guys, I'm going to jump.
Yeah, me too.
Appreciate
Too old
everything,
to stay
guys.
up to sleep.
Cool. All right.
Enjoy,
Well, I'll
everybody.
work on this recording here. It's probably going to take a bit, but yeah, good talking with you guys.
You
Thank
guys.
you.
Yeah, thanks for all the
All right.
tips.
Thank you, Chris.
Thanks, guys.
All right.
Yeah.